So that's about me. Fine. Now the topic which is given to me is from a deep learning neural networks, then convolutional neural networks, and precisely RNN. So more precisely, I can say it's about a computer vision and a natural language processing. Okay. So we are going to talk about vision and a natural language processing. But yeah, before going into that, I need to realize that how far and how much you are comfortable in machine learning. Like bring it down the agenda for today's session because I'm going to return, and then I think we are going to start with the introduction of deep learning, and then the backbone of a deep learning is considered to be a neural network. So that is what the main topic for today about a neural networks. Okay, so let me share my screen, guys, with you. And yeah, but definitely I will share let me delete this. So let me write the agenda first, then I will come on to the topic. Okay, so the agenda for like today's session is going to be the picture which you might like see. Okay, so that is about like AI versus ML versus DL. First thing is about like we are going to discuss that circle. Okay, about like AI versus ML versus DL. Then okay, this is the main thing because before starting anything we need to have a motivation. Okay, so why we are learning like because even before starting machine learning you definitely have some motivation in your mind. Okay, so why I'm learning this machine learning. Okay, so the same thing for a deep learning also. So before starting we need to understand that why deep learning is important. Okay, and or even more precisely I can say that what the major difference like between machine learning and deep learning. So why deep learning is important, so this is a very important thing. Then the third important thing we are going to discuss. Okay, so from here I'm going to start with the neural network, biological neuron versus artificial neuron. Okay, so even our artificial neural network, okay, so which we are going to discuss in this whole session, is inspired by a biological neuron, means the functioning of your brain. Okay, so that is what we are going to discuss, that works like a difference between those two. Okay, and then we are going to talk about like a perceptron model. Okay, so it can be a single layer perceptron, it can be a multi-layer perceptron. So we will I think like I'm allowed to take like a mathematical session. Okay, so I'm allowed to take a math okay, because this is going to be an in-depth session because we have like 4 hours. So I'm going to like show you mathematically that why we need to have like a multi-layer perceptron. Okay, so like a single layer perceptron is simple to easy to understand, and even it's easy to interpret. But then why we shift to the multi-layer perceptron? Okay, so in case of a perceptron, we are going to talk about both the things. Then the important thing is about like a forward propagation. Okay, so the whole neural network, like in the working of whole neural network, we have two things. We have a forward propagation and we have a backward propagation as well. Okay, and along with this we have like three important terms to discuss. Okay, so this even inside these three terms. Okay, so these three terms is going to be like these three terms like activation function. So we have an activation function over here, which is which I am going to discuss, activation function. Then a loss function. Okay, loss function. And the third one is optimizer. So all these three things is like definitely a part of like forward and backward propagation. But even I'm going to discuss about okay, so it is not about like I'm doing because in terms of a calculation I'm going to take maybe a single activation function, but I will tell you like about around 5 or 6 activation function, and like what are maybe the drawbacks and what are maybe the advantages of each and every activation function. The same thing with the loss function and the same thing with the optimizers. And definitely you definitely know about like some of the activation function. Like we have a sigmoid, so you know about a sigmoid function because you learn maybe those things in a logistic regression part. Then in a case of a loss function, we have a mean square error, root mean square error. So this is also one thing which we have already learned in case of like at a time of a machine learning, at type of a linear regression. Then in case of optimizer, we are going to discuss about we are going to took a like in-depth discussion of gradient descent optimizer. Okay, so I think this is also one thing which you have already done. Okay, so but yeah, we are going to talk in like more detail. We are going to talk with respect to a deep learning this time. Okay, and we are going to explore different activation functions, different loss function, as well as optimizers. Okay, so let's start with our first topic. Let's start with our like agenda. So our first topic is nothing but we need to understand what may be the difference between these three terms. Okay, so let me take that picture first over here. Okay, and even guys, I think yeah, all of you aware about at least AI and machine learning. Okay, so I think you all of you guys are already aware about these things. Okay, so 1 second, it may be AI versus ML versus DL. So yeah, guys. So half of your knowledge. Okay, so can anyone tell me about like what may be the possible difference? Not a difference, but just give me the definition of like artificial intelligence and like machine learning. Okay, although I know that maybe okay, so this is the first session for deep learning. So I'm not asking about the deep learning, but yeah, give me the definition of like artificial intelligence and machine learning.
Artificial intelligence, we try to mimic a human brain.
Yeah, okay, guys. So yeah, like regarding your regarding your session itself, I get a call. Okay, so yeah, let's make this session like interactive. I think for that reason only I asked you a question. Okay, so what let me know did you guys know about the difference or just the definitions of like artificial intelligence and machine learning, or maybe you guys can like just give a relation that how it is like AI like what are the things which we can call it as a AI, and what may be that what may be the proper definition for a machine learning. Then only we can come on to this subset of machine learning. Because deep learning is okay, apart from like so many other definition, I can simply say that deep learning is a subset of machine learning. Okay, so if I talk about first machine learning and artificial intelligence. So, what is your opinion about these two terms, artificial intelligence and a machine learning?
So I don't know the exact definitions, but when we talk about machine learning, we usually uh, basically there are some statistical models that we use in order to uh, infer certain things from the data
Information,
that
you
we
can say.
have.
Yeah.
We derive insights from some data and then use those insights in order to make predictions on new data. That is what machine learning involves. Uh, AI is something similar, but it doesn't necessarily involve statistical models. It can also be something like a heuristic, using heuristics or some other parameters. We can uh, build something that can describe the data that we have. Uh, so, for example, for example, like NLP or voice recognition, or like for example, recently we have this trend for something called DALI, basically making generating images out of text descriptions, things like that come under AI.
Yeah, image caption. Yeah, great. So yeah, it's a great definitely this is what actually I want to know. So like just a difference. Okay, so I don't want to get a like exact definition. And yeah, exactly the like yeah, it's exact definition. I think he said that machine learning is kind of a statistical model. Like we are trying to create or we are trying to build a statistical model which help us to get insight, or I can say the information from the data. Okay, and based on those information, based on those insights, we're trying to make a decision or the prediction for the future. Okay, so this is what like about a machine learning. Okay, so it just, I can say in a very simple word that it's a practice of teaching computers that how to get knowledge, or how to get information, or how to get insights from a data in order to make prediction or decision for the future. Okay, so this is like a simplest definition of machine learning. And in terms of artificial intelligence, if I want to make a connection between these two, okay, so because machine learning is also a subset of an AI, so if I want to make a connection between these two, so yeah, he's absolutely correct. But I can simply say that in terms of like whatever the models we have generated with the help of machine learning, okay, so like maybe you know about a credit like a fraud detection system, okay, or maybe you have built about a loan automation system, you have built maybe related to some like a medical if I talk about like a medical scenario, so maybe you have created a diabetes prediction, or maybe a heart disease prediction of like this kind of a model you have created. Okay, or even you have maybe created a recommendation system like just like a Netflix or maybe a YouTube. Okay, so after applying this statistical knowledge, okay, after applying like our statistical knowledge, or like after whatever the insights we have get, and based on those insights, whatever the model we have created, that particular model is like it turns out to be a AI application. Okay, so like your Netflix app, or maybe your Amazon app, like our Google Translator, or our like Google Assistant. Okay, so these are all the applications of an AI. Okay, so in a simple term, I can like in a very simple way, I can say that application which can do its own task without any human intervention. Okay, so AI is nothing but it's like application which can do its own task without any human intervention. That will be considered as a artificial intelligence. Okay, so these are like self-driving car. Okay, so these are all the applications of an AI. Okay, so whatever the model we have created, or which can give me some prediction or maybe a decision, so that actually like into an AI application. Okay, so that is your like AI. So even whatever the things we are going to build with the help of a deep learning, with the help of a neural network, that can also be considered as an artificial intelligence, applications of an artificial intelligence. Okay, so this machine learning and deep learning is a kind of a technique. It's a like a technique or technology which help us to learn the patterns, or I can say, yeah, learns a pattern or a relationship between a data set. And with the help of these techniques, whatever the things we have created, or whatever the models we have created, that models are like converted into an application, and that application is considered to be an artificial application of an AI. Okay, okay, so I think yeah, it is clear to everyone. Any doubt? I come on to the deep learning, but yeah, the relation or the connection between a machine learning and artificial intelligence is clear to everyone.
Yes, sir.
Yes, sir.
Yeah. Guys, did I slow down my speed, or it is fine?
It's fine, sir.
It's fine. Okay, thank you. Okay, wherever you think like maybe my speed is slow down, or it may be fast, so yeah, just write in the chat box, or unmute yourself and say. Okay, so now come on to the deep learning. Okay, come on to the deep learning. So in terms of deep learning, so like if I just take like a definition from our internet, so it is nothing but I think you also maybe you guys also go through those definitions. So that is nothing but it like which can maybe it's a kind of a technique which can mimic the human brain. Okay, so like I think I told this thing earlier that uh, uh, deep learning is something where the neural network is considered to be a backbone of a deep learning. Okay, on which neural network is something on which the complete deep learning like a fundamental, like whether it is a computer vision or whether it's a natural language processing. So all the like both of these things are depend upon the neural network, the idea of a neural network itself. And that a neural network, that artificial neural network, is inspired from a biological neuron, that inspired from a biological neuron. And biological neuron is nothing but it is just okay, biological neuron is uh, we are trying to learn from a biological neuron, means how our brain works, means how our brain react. Okay, so just like if I touch something hot, something cold, so I just push my hand back from that particular object. Okay, so the way my brain works, the way my brain responds, in a similar way they have created they have created this idea, they have generated this idea of a artificial neural network. Okay, so deep learning is something which help us, or neural network is something which help us to mimic the human brain. Okay, so we are trying to create a robot, or we are trying to create a machine, or we are trying to teach a machine so that it can work in a similar way, it can respond in a similar and a quick way, in which my brain way in which my brain work. Okay, so the way my brain response, or the speed of my brain response, so in a similar in a same speed, in a similar way, like that machine should work. Okay, so that is what we are trying to learn, or we are trying to develop in case of a deep learning. So deep learning is again, it's like a subset of an machine learning. Okay, so guys, I think I there is some noise, so just give me 2 minutes. I just stop that noise and I will come back. Okay, just two. Okay, guys. So I think now there will be no noise. Okay. So okay, where I am. Okay, I think on deep learning. Okay. So the deep and even this word, this word deep in a deep learning refers to the even the depth of the network. Okay, so I think after 2005, when we have our first maybe a social media platform, I think Facebook. Okay, so I think after 2005 a lot of data start generating. Okay, so the very first time a kind of a app was created, where we can which can store our a name and password. We are giving a lot of our information, a lot of our personal information to we are sharing a lot of our personal information with that app. Okay, and even that particular app Facebook is generating billions of data. Okay, so it start generating a more and more data after 2005. Okay, so and especially in India, you know that after 2016, when our internet becomes free. Okay, so when our internet becomes free, so if, again the more and more data start generating even from the common people. Okay, so there we use there we need something. Okay, because so even we need to understand that actually where we need to have this deeper network, where you need to have this kind of a deeper architecture. Okay, because if you can work with a simple idea, if you work with a machine learning, because machine learning is also maybe with the help of SVM, or then we have a k-means clustering algorithm, which can help us to perform a image segmentation task. Okay, but when we start generating a lot of data, when a lot of data start generated, so it is not possible. Okay, so machine learning algorithms, or a simple algorithm is not able to handle those amount of data. Okay, so that's why we develop something, that's why we created something which can handle those amount of data, that much amount of data. And that is where the people introduce this term, which is called a deep learning. Okay, and even yeah, definitely the because it's a subset of a machine learning, or even previously in 2006 people also called it as a modern machine learning. Okay, but the word deep was introduced just because they just want to have a deeper network. Okay, because we need to extract more and more information in order to recognize the correct image, in order to get the information from a video data, in order to get the information from audio data. Okay, so in order to get the information from you can say a big data, we need to have a deeper network. You need to have a deeper architecture. It is not possible with a solo architecture. Okay, so this is a very important thing, with respect to a deep learning. Now, okay, so this is like one important thing. Now, if I come to like a motivation that why deep learning is important and why we are going like a deeper inside like this deep learning. So there are two important things, guys. There are two very important things which actually motivates us to go around this like deep learning. So one is the first thing is I think you know that if I broadly categorize the data, okay, if I broadly categorize like data, so it can be we can have two kind of like a data sets. Okay, so one is called structured data, one is called a structured data, and another one is called unstructured data. Okay, another one is called unstructured data. Okay, so guys, any one of you can tell me the difference between a structured and unstructured data? Anyone having idea about this structured and unstructured data? I know that you very much familiar about numerical data, categorical data, then continuous and discrete data, time series data. I know that you are very much familiar about this, but yeah, if I broadly categorize it, so it can be categorized into two category. One is structured, another one is unstructured. So anyone can tell me about what may be the structured data and what kind of data can be considered as unstructured data? Okay, so let me ask like a simple question with you. Okay, so guys, I know you are familiar about a machine learning. Yeah, like you have done maybe a projects on a machine learning. Okay, you have created some classification model, some regression model. Okay, so till now, what are the different kind of data which you have handled? Maybe you have a data in a CSV format or maybe Excel sheet. So in that way, what kind of data like you have handled so far?
Only CSV and Excel.
Only CSV and Excel, or even but you know that it can be an HTML format also, it can be a tabular format also, and you can handle it.
Yes, sir.
Yeah, so structured data is nothing but whenever my data present in this format. Okay, so like a CSV format, or maybe an Excel sheet. Okay, or maybe a HTML, or maybe a tab separated. Okay, so even if you have a data in maybe a tabular format, so even that data is considered to be a structured data. Okay, now come on to the unstructured data. So unstructured data is very simple to understand. So nothing but like if we have images. Okay, so suppose kind of image classification task. Okay, so if I want to create a model which can recognize me and you as you, so that is nothing but a image classification model. Okay, or that person just said that a kind of a model is created which can try to generate a text from the images. Okay, so that is also kind of unstructured data. Okay, so images, or maybe we have a text data. Okay, so text data is nothing but we have a data in a textual format, like a review. Okay, kind of a review. So we are trying to give a review to like any product, or maybe whenever we go to the restaurants, we are trying to give a review to maybe what kind of a system they are having. Okay, so that review is a text data. Even the prescription written by a doctor is can also be considered as a text data. Okay, so images, then text, then a video. Okay, so video is also a kind of a text data, and audio. Okay, so whenever we have unstructured data, okay, so this is what I'm telling you, that why we should learn about a deep learning, why deep learning is important. Okay, so the very first thing is whenever we have unstructured data instead of a structured data, so my machine learning model not works well. Okay, so my machine learning model will not work well. It means it will not give me kind of a performance, okay, which I want to have. Okay, so it will not give me like a performance or kind of or I can say the desired output, or desired performance which actually like which I want. Okay, so maybe if I use a machine learning with the image data, so it can like classify me as you and you as me. Okay, so means a kind of a misclassification. Okay, so or maybe my accuracy will be around 40% or maybe a 30% or it may be a 50%. Okay, if I try to use maybe some machine learning model like SVM or maybe anything. Okay, so this is one thing which where I need to use a deep learning model. Okay, because in deep learning model we can use a deeper network. Okay, so it can extract the information from images, it can extract the information by going into a very deeper, and by getting those information it can easily generalize. Okay, it can easily create a model which can recognize me and you, and it can give me an accuracy around more than 80% or maybe 90% or maybe 100%. Okay, then the same thing with the text data, video data, and audio data. Okay, so this is the first place where we use where we need to use a deep learning. Now the second important reason to use like a deep learning, and the second important reason why this deep learning is important. So in case of a machine learning, okay, so guys, that the pipeline of a machine learning model. Okay, so I think every one of you aware about the pipeline of a machine learning model. So we try to pass an input. Okay, then with that input, we're trying to create a model. Okay, after passing that input, we're trying to perform a feature engineering. Okay, I think every one of you aware about a feature engineering or feature extraction task. Okay, so can any one of you let me know about feature engineering? What is feature engineering, or what may be the feature extraction or feature selection? Anyone?
Feature engineering is basically combining certain features or extracting certain features from a combined feature in order to make it more meaningful. Like, for example, if we have like a house with several floors, and for each floor we have a square feet information. So a more meaningful feature would be to combine, add up all the square feet and then have a total square feet feature, which is basically feature engineering.
Yeah, great. So like even when we have a categorical data, so we are trying to convert that categorical data into a numerical one. I think this is a very simple operations which you have already done in a machine learning. Okay, so converting a categorical data into a numerical one, then trying to handle the null values with maybe any statistical, trying to replace the null value with any statistical value, maybe mean, median, or mode. Okay, so yeah, these are all a part of a feature engineering. Okay, so even we're trying to select the best features. Okay, so maybe we're trying to perform a Pearson correlation, or we can try to perform a chi-square test. Okay, so to get the best features. Okay, to get the best feature from like a data set. Okay, so these are all considered to be a feature extraction, or you can call it as a feature engineering. Okay, so in case of a machine learning model, what we are trying to do, how we can create a model. So first we have a data set, we have an input data, then we are trying to perform a feature extraction. So this feature extraction is going to be a manual feature extraction. Okay, so we are manually trying to extract a feature. We are manually trying to perform this feature engineering. Okay, so with this input data, we are trying to perform a feature extraction, or I can say a feature engineering. Okay, and then with this extracted features means where we just scale up the data, like he said that if we have all the information in square foot, then it will be more meaningful. Okay, so a square foot means you just want to have all his data in a same scale. Okay, so if we can if my data set if my data is available in a different scale, so I can try to convert that data, or I can convert those data. I can try to bring all those data into a single scale. Okay, so yeah, so there we can perform a normalization or standardization, or maybe a log transformation, also any kind of a transformation we can do to bring my data into a single scale, a same scale. Okay, so this is what we have done in case of a feature engineering, in case of a feature extraction, to make my data more meaningful. Okay, more informative. And then with this new feature, I'm trying to create like a model. Okay, so we are trying to create a machine learning model. So like we are trying to create like a model. So maybe I can try to pass any machine learning algorithm. So if it is a regression task, so I can try to use maybe a linear regression, or if it is a classification task, so I can try to use logistic regression, or maybe a decision tree, or maybe a random forest index. Okay. And then with this model, I will try to maybe if I get any new data. Okay, so suppose if I get any new data, or maybe any information from the test data. Okay, so my model give me okay, so give me some prediction. Okay, so it give me like some prediction, and then I just try to compare this like a prediction, this predicted value with the actual value. Okay, so this prediction with the actual value, and this is where I try to find out a loss, or maybe I try to so loss is nothing but how far your predicted value is from the actual value, so that is considered to be a loss. Okay, so I try to get a loss, or I try to get an accuracy if it is a classification task. Okay, so this is whole this is a complete pipeline. Okay, so now the main thing which I need to notice over here, which I want to notice that in this case, in this machine learning pipeline. Okay, so in this machine learning pipeline, we have this feature extraction. Okay, so we have this feature extractions. We are trying to extract this feature manually. Okay, so suppose if we have a linear information, so suppose if we want like a linear, suppose my data set is linearly separable. Okay, so I just try to create a handcraft features manually. Okay, I just try to like create a handcraft features in a linear way manually. Okay, and if it is non-linear information, so I just try to put my data in a non-linear way, again in a handcrafted way. Okay, so this is what I'm trying to do in case of a machine learning. But in case of a deep learning, okay, so I can simply say that we have this fixed model, or I can say handcrafted features. Okay, so in case of this machine learning model, we need, okay, so in case of a machine learning model, in order to create a model with the help of machine learning, we need this like handcrafted features. Okay, so I can simply say that handcrafted features are required. Okay, so handcrafted features are required. So we just try to perform this like this thing manually. Okay, we just try to perform this thing manually. We're just trying to create a manual we just try to create manual linear data, or maybe a non-linear data. Okay, but so this is a drawback of or you can say of fixed model. Okay, fixed model based algorithm. Okay, but in case of a deep learning, or in case of a neural network, we have like this feature extraction takes place automatically. Okay, so maybe if you have an idea of a neural network, that how a neural network looks like. So suppose I have a picture of maybe a mine over here. Okay, so maybe this is like me. Now I just pass, okay, I just pass like my inputs. Okay, so this image is nothing but an input. Okay, so this image is nothing but an input. Okay, so now if I pass if I pass my image, so like here I have some like hidden layers. I have maybe hidden layers. Okay, and now this hidden layer is extracting information. Okay, so I will show you this like a picture on the internet. Okay, so in a case if you don't not aware about this like a picture, so I will show you this picture on an like internet now, but let me draw it first for you. Okay, so now, so like in this hidden layer. Okay, so this is nothing but a input layer. Okay, so this is nothing but a input layer, and this is nothing but a hidden layer. Okay, so these three are nothing but a hidden layer, and this is the output layer. So in this hidden layer, automatic feature extraction will take place. Okay, automatic feature extraction will take place. Okay, so this is again a reason that actually motivates me to learn about to go into a deep depth of this neural network. Okay, so this is again like one of the very important reasons. So the very first reason is nothing but where we have unstructured data. So machine learning is not helpful, or it is not giving me desired output in case of unstructured data. So that is the first reason. And second reason, that in case of a machine learning or in case of a fixed model, we require a handcrafted feature extraction. Okay, sorry, handcrafted features are required. But in case of a deep learning, automatic, this thing can be done automatically. Okay, so this particular thing can be carried automatically. Okay, so let me even show you the picture so that you can get okay, so let me show you the picture also. So image of a neural network. Okay, so yeah guys, this is how like this neural network will look like. Okay, so yeah, we have this hidden layer. So hidden layer is nothing but maybe an image of a cat, dog, or maybe mine. And then we have this like hidden layers in between, and this hidden layer is responsible for a feature extraction. Okay, so you don't need to create a handcrafted features. We don't need to do this task manually. Okay, and then it gives me an output. Okay, so these are the two important reasons. These are the two important reason which actually motivates me to learn about a deep learning or learn about a neural network. Okay, so yeah guys, okay, so we have cleared the first two agendas of the day. So yeah, let me know now like if there is any issue, or if you're not able to understand anything till now, or if you have any query.
No, sir.
Yeah,
sir.
guys, any doubt?
No, sir.
No, sir.
Okay, now come on to the biological neuron. Okay, so let me first see that whether the full picture is present or not. Okay, and even tell me guys, because I don't know that how like your class is going on. So even tell me that whenever you guys need a break, or whenever you take a break. So even like tell me. Okay, don't be worry about anything. Okay, so this is one of the picture. This may be the first picture. Let me see whether there is a synopsis. Okay, 1 second. Let me. Yeah. Although yeah, synopsis are present over here, but it is not showing in this picture. It is present. I just see it. So yeah, it is present over here. Yeah. So let me take this picture over there. One thing that I'm able to. So let me see where I'm having this synopsis. To put through some place. Yeah, I think this picture is fine. 1 second. Okay, so yeah guys, so this is yeah, biological neuron. If I talk about a biological neuron versus like artificial neuron. Okay, so guys, actually what happened like in like around okay, so this idea is was very old. Okay, so the very first perceptron which was introduced like it was around maybe 1958. Okay, so it was around like around 1958 when the first perceptron was introduced. So the researchers are very curious that like they just okay, so if you see the functioning of our like a brain, or if you see the functioning of like this biological neuron, so you can see that we have like these three things. We have a dendrites, then we have this cell body, and we have this nucleus. Okay, now what exactly happened? Okay, so now what exactly happened like with this network with this biological neuron? Okay, so you can consider this dendrite as like input. Okay, so you can consider this dendrite as an input. Now like these dendrites are like collected collected in a place. Okay, so like all the inputs. Okay, so means whatever the images we are like see, or whatever the thing. Okay, so just try to imagine yourself as a maybe 2 year of child, or maybe 3 year of child. Okay, so when we are like very small, when we are child, or when like when we are child, so we don't know like a lot of things. Okay, so maybe when we saw like maybe any image or maybe anything, so we are not like able to generalize it. We are not able to recognize it. Okay, so whether this image is of maybe apple or maybe oranges. Okay, so just like my son. Okay, so from his childhood, he's very much like maybe when he was just like 1 or maybe 8 months. So I gifted him like a ball. Okay, so I was try to play with him of a ball. Okay, so a cricket ball, like a plastic ball. Okay, so I just try to play with him like with that ball. Okay, now if any object, okay, whether it's a orange or whether it's a apple or maybe it's anything. Okay, so if he see anything which is like a round in shape, so he just try to call it as a ball. Okay, so that is what he like, because his mind is not developed so much that can recognize so many different things. Okay, so he just like his mind is able to learn that specific thing, that anything which is round in shape, that can be a ball only. Okay, so whether it's apple or whether it's orange, or if it's any object. Okay, so you can consider any object which is round in shape. He just try to call that object as a ball. Okay, so because right now he's just of like around 2 years, so his mind is not developed that much that can learn a lot of things, that can store a lot of things. Okay, but as soon as he may be of 5 or maybe 6, and later on maybe 10, 15, so his mind start developing. Okay, so the neurons inside his mind, the dendrites, and so with the multiple inputs which is going to store inside this nucleus. So his mind start like learning. His mind start learning, and his mind so he's able to, then he's able to differentiate between a ball and orange. Okay, so but it will take some time. Okay, it will take some time. So it will take that much of time, that it needs a lot of input. Okay, it needs a lot of data. Okay, so just like in case of image processing, or in case of image classification, we need a lot of data. Okay, so suppose if I want to create a multi-class image classification model for maybe, okay, so you guys okay, so how many people are present? Okay, so we have in total 12 participants are there. Okay, so suppose I want to create a model which can recognize each person with his name. Okay, so which can recognize Shivam, which can recognize maybe Amit, Amshira, or like Deepika. Okay, so which can Vishnu, Vishal. Okay, so which can recognize every person. So for that, I need to give a lot of images. Okay, lot of images of mine, lot of images of yours, like a Vishnu, lot of images of Deepika, lot of images of like everyone. Okay, so maybe 100 images of mine, 100 images of Vishnu. So I need to give like 100 images of each person. Then only my model is able to generalize, my model is able to learn. Okay, so this image, so now like after maybe giving 100 images, or maybe after training with 1,000 images, my model will be able to learn maybe if any like new image or new picture of mine comes into the existence. So the model is able to recognize, okay, so this image belongs to a Shiva. Okay, so this is what happened like in case of a biological neuron, in case of with a human brain also. Okay, so we just need a lot of dendrites. Okay, so dendrites can be considered as an input for a brain. Okay, then the place where these dendrites are like collected is nothing but like a nucleus. And then okay, so and then we need okay, so then there is one thing which is like you can say impulse. Okay, so this impulse is nothing, it activates your brain to give a output. Okay, so like if I talk about if I take an example, suppose I'm just sitting over here, and I'm teaching you, and someone just come and give like a tea cup on my table. Okay, and because I'm more I'm just trying to teach you. Okay, so uh, like by mistake, my hand instead of that handle, my hand touched that like cup. Okay, so as soon as my I touch that cup, my brain responses, and I just took my hands back. Okay, so see the same thing happened like with everyone. Okay, so suppose if someone give you a hard slap. Okay, so someone gives you a hard slap in your in your face. Okay, so you just you're just trying to respond. Okay, at the same time. Okay, so that response for that response, that impulse is responsible. Okay, so this impulse is responsible for that particular response which which brain is generated, or which we are trying to generate in that limited time. Okay, or in that exact time. Okay, so that is what happened in a biological neuron. Okay, so suppose if we if we got if we heard from everything, so my brain responds in a very quick manner. So that is that is because of this impulse, because that impulse is responsible for responsible that for that response. Okay, fine. Now uh, 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 by taking an idea from this biological neuron, people researchers had developed something called a artificial neural network, means artificial neuron, I can say. Now this artificial neuron is not the exact, so in this artificial neuron we are not having the exact thing. Okay, we are not having the exact same thing. Okay, but this is nothing but a approximation of this biological neuron. Okay, so anything can be approximation, cannot it cannot be an actual. Okay, it cannot be exactly the same thing. Okay, so by taking an idea, by getting inspired from this biological neuron, by taking an idea from this biological neuron, people create something which is which you can call as an approximation of a biological neuron. Okay, so this artificial neuron is considered to be a is considered to be approximation of this biological neuron. Okay, and now you can see that even you can consider this a dendrite as an input, and this nucleus is a place where some pre-processing takes place. Okay, as I told you about a hidden layer. Okay, where the feature extraction take place automatically. Okay, so same thing happen over here, and the same thing happen over here also. Okay, so some kind of a pre-processing will take place in between x1 and w1. So before reaching to this a summation. Okay, and then there is in between these two we are trying to build some kind of a connection. Okay, and in case of biological neuron, that connection can be established with the help of synapses. Okay, the picture which I'm just trying to show you. Okay, so synapses is responsible for making a connection to get the output. Okay, so here that and that impulse. Okay, so the in case of biophonia we have that impulse which is responsible for quick response from our side. So in a similar way we have activation function over here, which help us to which makes our neuron activate. Okay, which help us to give a response in a quick time. Okay, so the whole thing is inspired with this a biological neuron itself. Okay, so the complete process or the complete artificial neuron is inspired by this biological neuron itself. Okay, so yeah guys, this is a simple this is a simple definition or the connection between a biological neuron and an artificial neuron. Okay, now I will go through a perceptron and even the mathematics of because now the our calculations are going to start. Okay, so before starting a calculation, this is the whole theory about artificial neural network. This is whole theory about a deep learning. And let me show you that picture of a neural network, so that so we are going to build this particular model. Okay, so we are going to build this particular model, or I can take this kind of a model we are going to build. Okay, so we are going to take an input, then we are going to do some calculation. Okay, some pre-processing things we are going to do inside this hidden layer, which is responsible for automatic feature extraction, and then finally we get an output, means prediction. Okay, so the whole process, this whole process is considered to be okay. So let me take annotation. Okay, so this whole process, this whole a process is going considered to be a forward propagation. Okay, so this is called a forward propagation. Okay, so after doing a forward propagation means after doing some like a calculation over here, or I can say the pre-processing over here, I will get a prediction. Okay, we'll get a prediction over here, means our output. And after getting this output, we are trying to get the loss. Okay, means the error. Okay, so how much error my model is doing. Okay, so maybe the accuracy of my model is 80%, so I can say that error is 20%. Okay, so we are misclassified 20% of the images. Okay, so that error we are going to calculate over here, means a loss we are going to calculate over here. And then by using an optimizer, okay, so there is something called an optimizer. So by using an optimizer, I'm going to update a parameter in order to minimize this loss. Okay, because definitely we are not able to deploy this model if my loss is very high. If my loss is very high, so I'm not able to deploy it. So in order to minimize the loss, I'm going to update my parameters. Okay, so maybe you heard about this term, or maybe you have learned about this, like a gradient descent, or like convex function, all those things. Or if not, then we'll going to talk those things in detail. So don't worry. But that updation which took place over here is nothing but called a backpropagation. Okay, so this is called a backpropagation. Okay, so now we are going to talk about a forward propagation, means the calculation inside a forward propagation, and then calculation inside a backpropagation. Okay, so yeah guys, now okay, so it's my simple recommendation for you to take pen and paper, okay, or maybe your notebook, whatever you have, okay, along with the pen, so that you guys can do like a calculation along with me. Okay, and yeah guys, it's a very easy and simple and calculation. And since it's a foundation, because this neural network, as I told you, this is a backbone of your deep learning model. Okay, so whether going forward, whether we are going to create computer vision, means a CNN, or whether we are going to create a RNN, both the place you can see that the full form of a CNN is a convolutional neural network. So there also we have that neural network. And in case of RNN also, that is a recurrent neural network. So there also we have a neural network. Okay, so this is the foundation, this is the backbone of no matter what kind of task you are going to perform, whether it's text classification or whether it's an image classification. This is like your foundation. This is the main thing. Okay, so understanding the calculation of artificial neural network is very, very important. Okay, so let me start with the calculation. And before starting a calculation, okay, just let me know that till now if any doubt or anything you want to ask.
No, sir.
No, sir.
Okay, and I will give you very fine notes. Okay, so let me check that how I can share notes with you. So I have created like a Jupyter like in form of a Jupyter notebook. I have created like all these notes on each and every topic, like based on the deep learning, then loss function, optimizer. Okay, because I'm a researcher also, so I have a habit of writing research papers and blogs and all. So I have created like these notes, and I have stored in a Jupyter notebook. So let me check that how I can share with you. I will share, but I will definitely share like these things with you, these materials with you. It will be very, very useful.
Sir,
Okay.
it can be shared in the chat itself, Zoom chat.
Chat. Okay, so I think yeah, Zoom has have one like new feature now. We can share a file over here. Yeah. Yes. Thank you. Yeah, I just missed it out. Okay, I will share in a chat itself then. But it's a zip file. Okay, yeah, it's a folder, so I can create a zip and I will share. Okay, I will share. I will share in a zip itself. Okay. Okay, so just take an idea. Okay, so just start with a simple network, because doing a calculation with the multi-layer perceptron, or doing a calculation in a like complex network is not possible in this plain paper. So I'm just taking a simple, and I think you already know because you have already completed a machine learning, so you know that whatever the equation we have, we can generate, or whatever the equation we can create, that equation can be generalized for for 3D, 4D, and for any like a space, for any dimensional. Okay, so oh, fine. So yeah, this is the network I'm going to take, and in this like same network, you can see that we have this x1, x2. So these are nothing but my inputs. Then this w1, w2 is nothing but like my weights. So this summation. So here we are going to do a summation. So this summation is nothing but we are doing in with respect to this xi and wi. Okay, xi and wi, and my output will be what? So my output will be nothing but okay, and suppose if like all these weights are zero. Okay, so although this is not like every time your weights are zero, but just suppose that if all your weights are zero, so we need to have something to like in this output. So for that reason we have something over here is called a bias. Okay, so I think you are aware about this kind of like equation in a linear regression. You might have learned about this thing. So this is going to be my like output. So here we have a sigma, means activation function. So this activation function, so right now I'm going to use like a sigmoid activation function. So this is going to be a sigma. So summation of xi and wi plus beta. Beta is nothing but a bias. Okay, so let me draw it again, and let me show you the calculation for a forward propagation. Okay, forward propagation. And this is like I'm going to go with the single training example. Okay, so let me take like a single training example first. So single training example means in your data set you just have like a single row. Okay, so with the single training example, let me create like your forward propagation first. Okay, so I think this is my inputs: x1, x2, x3, and x4. So these are like, this may be my inputs in the first place. Okay, and this is where we are going to combine it. Okay, so now this is my I can say I'm taking a single training example. So x11, x21, x31, and x41. And the similar way, okay, so this w can be written in this way. So w11, w21, then w31, and w41. Okay, and we have a single training example. So even inside this bracket we have one. Okay, so here also we have one, one, one. Okay, so now this what this two values indicates. So this two value indicate that we have one single training example along with four features. Okay, so we have four features. So you can consider any data set where we have four features. So even like I think iris data set is having four features: setos, iris, seto, sorry, petal length, petal width, sepal length, and sepal width. So that you can consider over here. So we have four features, and but like right now we we are having a single training example. Okay, and then along with that like we have a bias over here, bias term also like included, and finally I'm getting an output y hat. Now this Z is kind of a nucleus. You can make a relation. So where I'm going to do a summation, and then this A1 is nothing but an activation function. So activation function can be used for two purposes. Okay, so the first thing is, I think I already told you that it's a kind of a response. It is like activation function is used for a response. Okay, so it is responsible for like quick response, or like to activates my neuron, or to activates these inputs. Okay, the first thing. And the second important thing is it helps us to normalize the data set. Okay, so suppose the very first example I'm taking, that sigmoid activation function. So as I told you that sigmoid activation function is sigmoid is also a kind of an activation function. So if I use a sigmoid anywhere, so you know that the output of the sigmoid is going to be in between 0 to 1. Okay, so doesn't matter that what may be the input value. So it can be 1,000, it can be a 10,000, it can be anything. But when I pass those value, when I pass those like summation, that value through this activation function, means through the sigmoid, so the final value is going to be in between 0 to 1. Okay, so I think you can understand that, yeah, it also help us to like even the normalization, or I can say a data transformation, or in a simpler way you can say that to bring the data in a similar scale. Okay, so activation function along with the along with the activation of the inputs, or along with the activation of inputs of the inputs and weight, it also responsible for a normalization of a data set. Okay, now even like just write out this like signatures. Okay, so I think I hope that this is maybe clear to you, but then also I will write down over here, so that it will be helpful for those who may not able to understand. So this K is nothing but example. So as I told you that we have a single example, so that's why we have this one throughout the inputs, and this J indicates the number of features. Okay, so we have 4 features over here. Okay, means this is nothing but a row, and this is nothing but a column of your data set. Now this if in terms of the main thing is like a weight, I need to understand. So weight wi is, okay, so here I can write I. So I is nothing but it indicates the current layer. Okay, the first thing is indicates the current layer. So right now we just have one single layer. Okay, so this is nothing but we are making this thing for a single layer perceptron. So this is a single layer we are creating, so that's why we have one throughout the weights. Okay, suppose if we have one more layer, like you already see the images. So suppose we have one more image, one more layer. So it can be 2. If we are like passing towards the next layer, so it can be 3. Okay, and then 1 means from where to where this is like going. Okay, so I'm going from like 1 to 1. So the like in the first layer itself, so that's why it's 1 1. Then I'm going from like 2 to 1, so that's why it's a 2 1, then 3 1, then 4 1. Okay, then if I talk about this Z1 and 1, means I can write in this way that it can be a Z I and K. So this J is nothing but again this I is nothing but a current layer. Okay, again it's a current layer. Then K is again example. I think we have already written about this 2 things. And here this J indicates that index value. Okay, index in that layer. Okay, and the same thing goes for this A. Okay, so the same thing goes for A. So whatever we have like whatever the notation we have this Z, the same notation goes for A. Okay, so I think yeah, every notations are clear to you. Okay, so the notation, so the main notation which we need to remember is for this X and W and Z. Okay, so I think this is because A is having a same notation just like a Z. Okay, so I think this notations are clear to you. Yeah,
Yes, sir.
Yes.
now let me do a calculation. So I think calculation is very easy to understand. So for a single training example, if I try to do a calculation over here, so what is that calculation? So that will be nothing but it will be W11 x1, and since we have a single training example, then it will be a w21 x1, sorry, x2, then w31 x3, and w41 x4, and then finally we have a bias. So this is my z. Okay, so this is my z, and if I try to perform a matrix representation, okay, so I hope that you like in a logistic regression and in a SVM you go with the vector representation or a matrix representation also. So if I do a matrix representation over here for this, so it will be nothing but it will be like can be written in this way. So z11 can be written. So guys, I think you know that like this weights and this w and this x is having a same shape. Okay, so in a vector representation they are having a same shape, so we can't go forward with the same shape. So that's why it will be represent after transformation. Okay, so w transform then x n plus b1. So this is how we can represent this thing. Okay, so this is how we can represent. And now if I try to get a shape of this thing, so the shape of this w1, so previously the shape is 4 cross 1. Now when I transform it, so it will become 1 cross 4. It will become like a 4 cross 1 already, and we have like a 1 cross 1 over here. So now the final shape of my summation will be what? So it is going to be a 1 cross 1, means a single value I'm getting over here. Okay, and in a similar way, in a matrix representation, if I want to represent my a, so that a is nothing, so even this is also having a same shape, that is 1 cross 1, and it is going to be nothing but okay, so if I try to write a1 1 over here, so this is going to be a sigma of z1. Okay, so this is going to be a sigma. Sigma is nothing but is a representation of activation function, or you can say or you can simply call it as a sigmoid function. Okay, so this is nothing but it is going to be a so and the shape is going to be the same, that is not going to be changed. And this is nothing but my y hat. Okay, because this is the output, this is the final output, because whatever the value we are getting over here, that value is considered to be a probability, that will be considered as a probability. Okay, so maybe if I pass any input, so what may be the probability of this input belonging to any particular class. Okay, so this is a matrix representation for a single layer perceptron with a single example. Now if I take a multiple example, if I consider a multiple example, so nothing is going to be changed. Okay, so we just generalize the same equation. We need to generalize like the same equation for multiple examples. So suppose if I have a multiple training example, so if I have multiple training example, so suppose if I have a multiple training example, so at that place what I'm going to do, so in case of multiple training example, what you guys can do, so as I told you that it is like you can consider it as an Irish data set where we have 4 features and we have 140 example, sorry, 150 examples, or I think 150 rows are there. Okay, so in a similar way, you can take maybe n number of examples, or you can simply take maybe, for now you can take maybe 4 example or 5 example. Okay, so suppose if I take maybe so if I take a value of maybe a 5, or okay, so let me take like some value, or maybe take it as like 4. Okay, so now how I'm going to represent it? So this w will be represented in a similar way. Okay, so this w is going to represent in a similar way. Okay, so this is going to represent in a similar way. So w11, then we have a w21, then a 31, because we are having like 4 features only. Okay, so we are having a 4 features only. Fine. Now where I'm going to bring a change, so that change will be inside this x. Okay, means input, because this is going to be same 4 cross 1. Now this is going to be, this is going to change. Okay, so previously I just have like x11, then x21, 31, 41. Now I'm having like multiple values, so it can be written in this way. So x11, then I'm having x21, then it can be any value, so xn1. Okay, now here it will be x21. Oh, uh, sorry, x1, this is one itself. Yeah, x12. Okay, x22, and again it is going to be a xn2. Now the third is going to be a x13. So this is the third example, x23, and again this is going to be a xn3. Now here it is going to be a x15, then here also it is going to be a x25, and then finally it is going to be a xn5. If it is if I confirm with the 5 example, otherwise I can take maybe like m over here. Okay, for a generalization I can take a m over here. Okay, and then I can take maybe I can take m as 5 and n as 4. Okay. So like this is a generalization form of like this input matrix. Okay, so this is a generalization form of like this input matrix. Fine. Okay, and then this is how we can represent my x over here. Now if I want to take that z value, okay, now what will be the z value? So for a single training example, the z value will be like this. Okay, so I know that for a single training example the z value will be like this. So w11, then 1, and then x11. Okay, so this is the first value, and in a similar way w21, I know I hope that you know the like rest of the thing. Then a w21 x2, then w31 x3, w41. Okay, so because we are having a 4 examples, so w41 and x1. So this is for the first example, okay, with 4 features, and then again a b11. Now for the second example, it is going to be a z1, and since we are this is about second example, so this is going to be a w11, and this is going to be a 2. Okay, then x1 gain 2. Okay, and it is going to be a w4. Okay, it is going to be a w41 and 2, and x1 and 2. Okay, and the the same change with the b. Okay, so b1 and 2. Okay, the similar thing goes for till a z5. Okay, so z1, and this is going to be a 5. Okay, so w11, and here we have a 5, x1 5. Okay, so in a similar way it is going to be w51 5, and w1 5, and plus b1 1 and 5. Okay, because we have 5 training examples, and it can have like n number of training example or n number of training example. Okay, so now the same thing is going to do with a1. Okay, because the same equation we are going to write for activation function. So suppose for first activation function, means for the first value it is going to be a11, so it is going to be a z11 for the second. Okay, so a1 and 2 for the second example, it is going to be a sigma of z1 and 2, and similarly for third, fourth, and fifth. Okay, now if I try to write in a vectorized form, so how it will be, how I can write this thing in a vectorized form. So in a vectorized form, the very first thing can be written in this way. So z11, now this vectorized form is easy to understand, so it will be nothing but w11 full transpose into x1 and plus b1, and a11 is going to be sigma The second is going to be, I think now you understand. Okay, so this is going to be a 2, then 3, then 4, then 5. Okay, and if we combine all this, if we combine like 1 2 3 4 5, means A B C D E, if we combine all this, so by combining all these, what we'll get like Z11. So this is going to be a W11 whole transpose into X plus B11. Now what will the shape of this thing? So I think we know the shape. So shape of this is not going to change because it is 4 cross 1. If I transpose it, so it becomes like 1 cross 4. Now the shape of X is what? So X, the shape of X is nothing but 4 cross 5. Okay, and the shape of B1 is going to be 1 cross 5. Now what will the shape of this? So the shape of Z is going to be 1 cross 5. Okay, so this is a vectorized implementation, guys. Okay, and I think the same shape is for like activation function also. So the same shape is for A1 also. So if I write a shape for A11, so it is going to be the same. Okay, so it is going to be like a sigma of Z11. Okay, so now here also the shape is going to be same. Okay, so now if you generalize it, okay, so now I am going to write a generalized form, and this is the main thing which you need to remember, or you need to like store like somewhere. So if I generalizing above equation, or if I generalize all the things which we have done earlier above equation with, I can say m number of inputs, or I can say m number of examples, and n number of features. Means we can have a multiple features. It is not possible that always we have just 4 features, or it is not possible that we always have just 5 inputs, okay, or 5 examples. So in that condition, what will be the equation? So I think now you can understand this condition very well. Okay, so this is going to be a W11 transpose into X plus B1. And now if I try to write a shape, so the shape is going to be nothing but 1 cross n, because the number of features are n. X is going to be a m cross n. Okay, and now this is going to be a 1 cross n, and the final Z value is going to be 1 cross n. Okay, and now guys, this so now right now I'm just checking a one single hidden node. Okay, so I will tell you about what is a hidden node, but this value indicates towards a hidden node. Okay, and now I think you already know about MNN. Okay, you already know about MNN. So this is a vectorized implementation of this value. Okay, so this is the equation for a single layer perceptron, guys. So always remember that this is the equation for a single layer perceptron, or even with the single node. Okay, single hidden node. So what is the meaning of single hidden node, guys? So the single hidden nodes means we can have a multiple inputs, or we can have a multiple features, but we have this a single node over here. So not only a single layer we are having, along with that we are having a single node. Okay, so this is the simplest architecture we are having. Okay, so here we can have a multiple nodes, like we have 3 nodes. Okay, so I think like you see the pictures, so we can have a multiple nodes. Okay, so but right now whatever the equation we have derived, okay, so the equation which we have derived, that equation is for us like a single layered perceptron. That equation is for a single layered perceptron. Okay, is that is a derivation of a single layer perceptron with a single node. Okay, now in a single layer perceptron also, we can have a multiple nodes. Okay, so in a single layer perceptron also we can have a multiple nodes. So now the next thing which we are going to observe, that what may be the possible equation, or what may be the generalized equation for when we are having a multiple nodes. Okay, so guys, yeah, just quickly try to get through this equation. Okay, or if you want to, maybe if you want me to go down the like previous pages, I already have this note. Even I shared this, this is my own handwritten note. So even I shared this note on a LinkedIn also, my profile also. So I will share this PDF with you, don't worry about that. But then also, if you just want to observe this equation once, so yeah, just tell me. Okay, so I just get onto the first page and then try to come on to this page. Yeah guys, okay, so you want me to go back to the starting with the start equation. Hello. Hello guys.
Yes, sir.
Okay, so are you guys able to understand this equation which I have took like right now? This, the equation for a single layered perceptron is like clear to everyone,
Yes,
or any doubt?
yes, sir.
Okay, be frank. Like if there is any doubt, like if you're not comfortable with the math, maybe if you think that I am little bit fast, so yeah, tell me any doubt or anything if you want to say.
No, sir.
Okay, so this equation is clear to everyone, although I think this equation is very easy. uh, okay, so now this is with the single layer perceptron with a single node. Okay, now I just want to exceed this thing, because this is a very simplest thing, but I just want to exceed, I just want to like extend this knowledge for a multiple nodes. Okay, so suppose I have a multiple nodes, maybe if I'm having this kind of a scenario. So okay, so I'm taking a multiple example as a multiple inputs. That's why I'm taking an I over here. And even I will take like for a multiple out like a features as well. Now, instead of a single hidden node, so now we have a single hidden node. So, but instead of single hidden node, I'm going to take one more like hidden node. Now you can see that notation is going to change over here. So this is going to be a 2. Okay, and this value is not changed at all because we are in the same layer. We're not in the second layer. Okay, we are in the same layer, so that's why this value is unchanged, but this value changed. Okay, because this is the second node, this is not the first node. Okay, so this is how this picture will look like. It will be yeah, because like my drawing is not that much great, but yeah, I think this is understandable. Okay, and then from here maybe I can say that we have like um, output, output, so it can be anything. And even we have like w11, then if I go over here, so it will be a w12. Similarly here we have a w21, and then it will be a w22. Okay, similarly for 3 and 4 and then n. Okay, so this is like a single hidden layer, not we don't have like multiple layer, we have a single layer, but we have a two hidden node. Now if I try to write this equation, if I okay, I just tried based on the previous learning itself. Okay, not I'm not adding anything new, I'm not adding any new information, any new knowledge. Based on my like a previous knowledge itself, if I write the equation which I have written for a single node, so that will be what? That will be nothing but Z11, and it will be nothing but W1 1 whole transpose into x plus b11. Okay, now if I try to write the shape, so it will be 1 cross n, then it will be m cross n, and then it will be a 1 cross, and as here also we have 1 cross n. So this is for like node 1, and 1 second, let me write it for activation function also. Okay. So this is for like node 1. Now if I try to write for node 2, so it is not going to change at all. Okay, they're not going to change at all, so only the notation is going to change, rest of the things are same. So this will become a w2 then transpose x plus b and 2. Okay, so even the shape here also the shape is going to same, it is going to be a 1 cross n. Okay, so this is for like node 4. Okay, and like guys, in a similar way, so suppose if we are having a n number of hidden nodes, suppose if we are having a p number of hidden nodes. Okay, so like if I try to generalize this whole thing, if I try to, because we need to combine it. Okay, so if I combine this like the equation from both the nodes which I have written separately, so if I try to combine this, okay, if I try to combine this with a p number of hidden nodes with which m number of examples and n number of features. Okay, so this is nothing but this indicates my like number of hidden nodes, this indicates like my number of training example, and it represents my like number of features. Okay, so if I combine based on these like three things, so my final equation is going to be nothing but it is going to be a z 1, and now this w. Okay, so now I'm writing a w in a different way because this is a combination of all the w's, so it will be written in this way because we have different w's now. Okay, we have like w over here or w over here also, so just for the simplicity I'm writing because maybe you guys can confuse. Okay, so I can write a w in this way, then x, and it will be a transpose, sorry, it will not like going to be a okay, the transpose is understandable, and then b1. So now if I write a shape, so now this is nothing but a p cross n, this is going to be a m cross n, and this is going to be a simple. Okay, so p cross n, so the final is going to be a p cross n. Okay, so here also we have p cross, sorry, p cross m, I guess. Okay, and now this p is nothing but a hidden nodes. So we may have a multiple hidden nodes, so it not like just we have 2 nodes or 3 nodes, it may have. Okay, so even like guys, when we learn about a CNN, so I will show you that even we are using around 4,000 nodes also. Okay, so in a single layer we are using a 4,000 nodes also, so it's not like we just have 2 nodes or 3 nodes, we can have like 4,000, 3,000, 1,000 hidden nodes also. Okay, so yeah guys, this is it from a single layer perceptron. Okay, so with a single node, and this is with a multiple nodes. Okay, so this is also a equation for a single layer perceptron itself, but this is with a multiple nodes. Okay, now guys, now let's take a motivation for a multi-layer perceptron, because this equation seems to be very simple, and even if I try to, because, and this is what we are trying to learn in like in terms of forward propagation. Okay, so we are just trying to go, from this place to this place. Okay, we are just okay, we are just getting an output right now. Okay, we are not updating our parameter, we are just getting this output. Okay, we are not updating my parameter. Okay, so this is with respect to like a single layer perceptron. Okay, now why we need a multi-layer perceptron? Okay, so I will show you the reason. I will show you the reason because now I'm going to write an equation for a multi-layer perceptron. But before writing an equation for a multi-layer perceptron, it's important to understand that why we need this multi-layer perceptron. Okay, so like which kind of a problem or which kind of a scenario where we can't use a single layer perceptron, or which like what kind of a scenario where single layer perceptron is not able to help us. Okay, so let's check that scenario. So let's first take a motivation, and then I will show you that a calculation for a multi-layer perceptron. Okay, so yeah guys, before that, before going to a multi-layer perceptron, yeah, if there any query or any doubt you want to ask. And yeah, go ahead, let me drink some water also. Yeah guys, any doubt?
No, sir.
Once again. Hello. Okay, guys, am I audible? Hello.
Yes, sir.
Yes, sir.
Yeah. Okay, guys. So yeah, sorry. Stop. Okay, fine. Mm, yeah. Come on to the motivation for multi-layer perceptron. Okay. So I will explain this thing in a very simple way, maybe. Yeah, because you know about the logic gates. Okay, so yeah, I think guys you know about the logic gates like OR gate and gate. Okay, so can anyone of you like tell me about like OR gate and maybe AND gate? These are the simple logic gates which running with the boolean values. So what is the significance of a OR gate and what is the significance of a AND gate?
In AND gate, both the inputs need to be true for the output to be true. In OR gate, if either input is true, then the output is true.
Yeah, correct. Okay, so let's with the help of a AND gate and with the help of a OR gate. Okay, even I we don't need to take both the example. Even single example is like enough to understand. Okay, so with the OR gate or even with the AND gate, like we can understand what is the final capacity or what may be the like strongest capacity of a single layer perceptron, because you see that it's a linear combination. Okay, it's a linear combination of weights and inputs. So we can this is where we have we can go through it we can use a single layer perceptron where we have a linear separable data. Okay, just like in case of a logistic regression where we have a linear separable data where we don't have more complex data even with respect to a regression task also, because neural network can be used for both. It can be used for a regression and even it can be used for a classification task. Okay, so let us first check the capacity of a single layer perceptron. So I think you all aware about a gate, as she already said that if we have if our both the inputs are true, then the output will be true. Otherwise, it will be false. Okay, so in case of a AND gate. Okay, so if I want to draw a AND gate, maybe. Okay, so suppose if I can draw a AND gate in this way. Gate. Okay, so we have X11. One, and then finally we have an output. So like it can be my 1, 2, 3, 4. So we have maybe a 0, 0, then 1, 0, then 0, 1, and then 1, 1. So in case of AND gate, in case of AND gate, we have 0 over here. We have 0 again over here. We again have a 0 over here, and we just have 1 over here. Okay. Now if I try to make this thing, so it means what? Suppose this is my x1. This is like my x2. Okay, and let me take this y at 0, maybe at this point. Okay, so this is this is at 0. So at 0, 0. Okay, so at 0, 0 my output will be what? So at 0, 0 my output will be 0. Okay, now at 1 0. Okay, so suppose I can take like for x-axis I can take 1 over here, and for y-axis I can y-axis I can take 1 over here. Okay, and in the middle I have like 1 maybe 1 1 over here. Okay, so like in case of a 0 0, my output will be 0. Okay, so like this, so y I can represent with the like output. Now in case of a 0 1 0, okay, so in case of 1 0, okay, so again my output will be 0. Okay, again my output will be 0. In case of 0 1, again my output will be 0. Okay, again here also my output will be 0, and in case of 1 1, my output will be 1. Okay, now if I want to create a boundary, okay, so now we have like two classes. Okay, so you can see that we have two classes. One is like one. Okay, so we have two separate classes. One is one, and another one is zero. Okay, so if I want to create a boundary, if I want to create a boundary which can separate these two classes, so yeah, this is completely possible over here, that I can create a boundary. I can create a boundary, and this boundary you can easily separate these two classes. Okay, so this boundary is possible in case of a AND gate. Okay, means if we have data linear, if my data set is linearly separable, so I can easily create a boundary with a single layer perceptron. Okay, so suppose if here in this case, if you are using a single layer perceptron, so I can easily create a boundary, means I can easily make a like a classification between like two different classes. Okay, between two separate classes. Fine. Now so this is what happened. This is the capacity of a single layer perceptron. Even if you have a OR gate, okay, so suppose if you want to try to understand this thing by yourself, so suppose like you can take an example of a OR gate, or even you can take an example for a NOT gate. Okay, so I hope you know the like a value inside a OR gate and a NOT gate. So you can draw this like OR gate and NOT gate, and then you can draw this this curve, and then you can understand the log. You can understand that, yeah, in this scenario, your single layer perceptron will work. Okay, your single layer perceptron work fine. Okay, now in case of another like if we take another scenario. Okay, so suppose if I take another scenario, if I take a XOR gate. Okay, or maybe yeah, if I take a XOR problem, or maybe XAND problem. Okay, so in case of a XOR problem, okay, so suppose if I take a XOR problem or XOR gate, if I talk about, okay, so any one of you can let me know about an XOR gate, that what is the input and output of an XOR gate. Okay, so here we simply need to ask this question to ourselves, that can or whether a single layer perceptron solve this problem. Okay, and yeah, well, I guess any one of you can tell me about XOR problem.
If both inputs are same, then it is false. If both inputs are not same, then it is true.
Yeah, correct. Okay, so if both the inputs are same, means if you have a 0 and 0 as your input, so and maybe 1 and 1 in your input, so then your output will be 1. Sorry, your output will be 0. And if your inputs are different, it's 0 1 or maybe 1 0, then in that condition your output will be like true. It means 1. Okay, so this is a like a kind of a truth table for XOR problem. So let me draw it first for those who may not know about this. So let me create a table for you guys. So it can be X11. Now it is going to be a I1, 2, 3, and 4. Now a 0 0 will give you a 0. 0 1 will give you 1, 1 0 again give you 1, and 1 1 give you 0. Okay, now if I try to create this, if I try to create this, so again we have a x1 over here and x2 over here, and again we have our values at the same place. So this is my one output where like both the values are 0, and this is my second output where both the values are like 0. Okay, so this is also 0. Now at this place we have an output as 1, and again at this place we have an output as 1. Now yeah, now can I create a linear boundary to create a boundary, sorry, can I create a form a linear boundary to separate these two classes,
No, sir.
guys? No, yeah, is it, this is not possible in this scenario? Okay, so it is not possible to create a linear boundary over here. It means that your single layer perceptron or a single layer perceptron cannot solve this problem. Okay, so it's simply like since the linear boundary can't do like classification over here, so we need to add a non-linear boundary. Okay, so we need to have a non-linear boundary. So in order to have a non-linear boundary, in order to add a non-linear boundary, we need to adopt, or we need to go for a multi-layer perceptron. Okay, and even in every case, even in like any real world scenario, in any real world scenario where we have a image data, like we have some like maybe images, or maybe we have videos, or maybe we have audios, or maybe we have a text. So in like with respect to any real world images, with respect to any real world data, we need to we need to have a multi-layer perceptron. Okay, we need to definitely those data are, we can't expect that those data is the linear separable. Okay, so definitely those data can be a non-linear separable, and we need a non-linear boundary. Okay, we need like a non-linear boundary to solve those kind of problem. So that's why we need to adopt like this thing which is called a multi-layer perceptron. Okay, so this is guys, this XOR problem gives us a motivation for a multi-layer perceptron, and even we can check this thing with the regression point of view. Okay, so like this is we are able to check with the classification point of view. Even you can check this thing out with the regression point of view. Okay, so that's fine, guys. Let's go through my PDF, which I'm going to share with you. And yeah, definitely, if you guys have any issue or any problem, like in that PDF, maybe if you're not, although I'm taking every questions, okay, but like I have written just two equation, then create a dots over there. So like if you maybe stuck anywhere, so yeah, definitely ask me. Okay, now come on to the multi-layer perceptron. Okay, so now come
Sir,
on to the multi-layer perceptron. Yeah.
sir, actually, so I understood how like these OR and XOR gates are being used to create either linear or non-linear boundaries, and then in case of a single layer perceptron, we are not able to use XOR to create a linear boundary. But how is this relevant in terms of a actual perceptron? Because so before when you explained the perceptron, the activation function was a sigmoid. uh, so here, how are the functions different in this case?
No. Okay. One second. Can you just one more time just repeat your query? Uh, I'm not getting
So
completely.
so
Yeah.
in the node, so we
Mm-hmm.
basically had an activation function, which
Yeah.
was
Yeah.
the sigmoid function.
Okay. Yes.
And after that, you explained to us the AND, OR, and the XOR function.
Mm-hmm.
How are these AND, OR, and XOR functions relevant in terms of
Activation
perceptron?
function.
Yes, yes, in terms of
Okay, okay, okay. No, no. Why? Yeah, these things, this AND gate and XOR gate, which I have just taken right now, is not relevant with respect to that activation function for now. the way I have taken those things over here. As I told, like I think maybe you missed out that thing, that I'm just for checking that capacity and just for like motivation, I'm taking this example. Okay, I'm just taking this thing as an example. Okay, so in case of here, as I told her, like in case of this AND gate. Okay, so I'm just taking this example, or definitely here also you can use that activation function, like a sigmoid activation function. So suppose if you want to like code this thing, or if you want to see the code of this thing, so that code is also like even available. So even with this 0 0 1 0 0 1 1 1, you can apply your activation function, you can apply your sigmoid activation function, that is not an issue. But for time being, or for now, I'm just taking this and or for an example, for a reference, that where suppose if I want to give a motivation with the regression task, in regression term of view. So as I can use a sinusoidal function, like a sin x function, or a sine wave, or maybe a cos function, or cos wave. Okay, so that is what like kind of example, like I took an example of my child. Okay, my son. Okay, so that is definitely not relevant with this same sigmoid function, although for this 1 second. Arey yaar, कहाँ चला गया? Although for this XOR gate, or maybe OR gate, we can easily apply activation function over it. But this is like something I'm just taking as example, that here we need to create something like this, because here a non-linear boundary is possible, only linear boundary is not possible. So this is just with a kind of example to understand its capacity. Okay, I'm not I'm not connecting this thing with any of our equation which we have derived earlier.
Okay, sir.
Okay,
So
yeah,
this is just to explain
this is
why
just to
the
explain
requirement
that
for ML.
because I think you understand now, you understand the capacity now.
Yes, sir.
So just to take a motivation, that why we should learn a multi-layer perceptron, like this is I think this kind of a query you always need to arise in your mind, that anything new, anything new, when you start learning anything new. So every time you need to ask a query to yourself, that why this thing is relevant, why this thing is important, why we need to learn about this thing. So that's why I'm taking a motivation for a multi-layer perceptron, that because you see that the equation for a single layer perceptron is very very easy, then why we need to make it a complex, why need to add more layer? Because if you add more layer, so definitely the equation becomes a complex, it becomes a complicated, it's become a large equation. Okay, and then at the time of backpropagation, I need to find out the derivative. So like suppose if you are having 3 layers, so I need to find out derivatives up to 3 layers. Okay, so why we need to make it complicated if we can make everything with a single layer perceptron? So that's why I take this example. Okay, bhai,
Okay, sir.
clear? Now clear?
Yes, sir. Yes, sir. Got it.
Yeah. So, and even okay, this is a great thing that you guys are asking this question because you maybe you want to see the relevancy. Let me check. Yeah, I have the same notebook also, where I have this code also. Okay, but yeah, this may be quite confusing for more of you, so that's why I'm not taking right now. But yeah, I will show you this code also. Okay, with respect to the OR function, AND function, XOR function, and all. Okay.
Okay, sir.
Okay, fine. Now let's come on to the, okay, so let's go through a quick continuation with the class first. Okay, so now let's come on to the multi-layer perceptron. Okay, multi-layer activation neural network. Okay, so first I will give you the equation for a forward propagation. So this is everything which we have derived till now. It is with respect to a forward propagation only. Okay, so multi-layer perceptron, or multi-layer multi-layer neural network also you can say. Okay. It's fine. So how it will like represent. So I think this picture you have already seen. Okay, this picture you have already seen, but my job is to create at least one. So I'm not going to take multiple value over here. This may be n number of inputs I'm having, I number of inputs and n number of features I'm having. Then I'm having maybe this hidden layer. Okay, this should be a large circle. Otherwise, we don't have our key values. Okay, hidden. Okay. So this is my first layer and this is my second layer with three hidden nodes. Okay, so I think guys now you can see that we have three hidden nodes. Even I can say that we have key hidden node because this is going to be in this way. Okay, so now here we have this Z11 A11. Now this is going to be a Z21 A21 and this is going to be a ZP1 and AP1. Okay, so this is the first hidden layer. Okay, so with a P hidden nodes you can say. Now here what I'm going to write, so this is going to be a Z12 guys. Okay, I think now you can understand why it is 2 because we already written a notation. Okay, now this is going to be a Z22 and A22 and this is going to be a ZQ, sorry, 2 and AQ. Okay, now this is a P number of hidden nodes we are having over here and Q number of hidden nodes. Now it can be like more layer also. It can be a more layer also. Right now we have just 3 layers. Let's connect this node. Okay, although like in a real scenario, in a real like a neural network, we have like all these nodes are like interconnected. Okay, where we are not we are not like we are not trying to use a single information. Okay, so that's why all the nodes are like interconnected with each other, just like this, just like this. Okay, so definitely map but yeah, I think it is clear to you. Okay, now just okay, now let me write the equation, and I think even this equation, because the equation for a forward progression is never going to be like tough at all. Okay, and even for us it is not going to be tough because we understand with a single training example. Okay, because like I always see that somewhere people are trying to take take with a multiple example first, and so it will become like hard to generalize for a student. But I think we started with single training example, so I think now you can generalize any equation very quickly with respect to forward propagation. Okay, so let me write. This is for the first layer, so that's why I'm writing like a first over here. So for the first layer, we have p number of nodes, p number of hidden nodes. So I think you already know the equation for this. Okay, so it will be a W transpose, and W will be like this. If the W will not like this, so it will be a transpose. Okay, always remember. Then X and then BY. Now guys, just try to generalize it very carefully because you are going to see a very kind of a change in the second node, second layer. Okay, now the shape for this is going to be P cross N, I guess. Yeah, then it is going to be n cross m, and this is again going to be a p cross n. So the final shape will be p cross n. Now with respect to the activation function, it is going to be w, sorry, yeah, calico. This should not be a w. Z1, and again the shape is going to be same, so I'm not going to write it again. Now with the second layer, okay, now this is important. With the second layer, what is going to be my equation. So this is going to be, again we have a w2 over here, we have a w2 over here. Now here I can't take a x. Okay guys, so anyone of you can tell me that what value I can give over here, because I can't take as x is nothing but an input. So that input I already pass. Okay, so this is nothing but a x. Okay, so this is something which I already pass, and now I'm getting an output over here. So for this layer, what will be my input?
The activation function.
Correct. Yeah, activation function. So the output of this layer, the output of this layer will become an input for this layer. Simple. Okay, so it means that in place of x we should have like a1 over here, and then and the same goes for like, okay, and even here the equation is going to be same. So this is going to be a q cross p, then we have a p cross m. Okay, so p cross m, and then q cross m. So this is going to be a q cross m. So my activation function, check. Sorry. Okay, so by this is what my forward propagation, and this is we have created for a two layer. Now I think I think that you guys are definitely you guys are clever enough to generalize it for a multiple layer. Okay, so it can be a three layer, it can be a four layer, it can be a five layer. But yeah, now I know that what we so okay, so nothing is going to be changed for the next layer. Okay, so suppose if I having a next layer maybe z3, so for that layer in place of a1 it will be a2. Rest of the thing are going to be same. Yes.
So
Okay, so this is going to be your the whole calculation inside of forward progression. So now if I try to represent this thing with a computational graph. Okay, so let me represent this thing with a computational graph. It will be like more easy to understand. So this is nothing but a z11. Then we have like a1 over here. Okay. Then the second, I'm going to take over here. Okay. Now W2 is my weight, and the input is nothing but A2. Okay, so the input is nothing but this A1 for this. So this is what we can understand from this computational graph. Now it will give me multiple outputs definitely. So in this way I can write it like it can be A12, then it can be A22, be a multiple. Okay, the number of hidden nodes we are having. And then we are going to calculate the loss, because loss is nothing but a difference between actual value and the predicted value. Okay, so maybe we are having a actual value over here. So this is my true value, or maybe a ground truth I can say. So this is my true output and this is my predicted output. So this loss function is going to so with this loss function I'm going to calculate a difference between these two. So this whole thing, this whole process, okay, so the process which help us to reach at this place. Okay, so this whole process which help us to reach at this place, whatever the calculation we have followed, whatever the like equation we have done, so the whole process which help us to reach up to this place is called as a forward propagation. Okay, so guys, now yeah, let me know if anyone having any doubt with respect to a forward propagation. Any doubt, guys? Anything you want to ask? Okay, so the calculation with respect to activation function, the calculation with respect to a summation function. So I think now each and everything is clear with you. Okay, so in place of input you can have anything. Okay, so you can consider iris data set, you can consider maybe your churn prediction data set, even you can consider any image data set. Okay, and now the next thing which we are going to discuss is about a back propagation, because definitely no model is can give me 100% accuracy, or it will not it may not be like 100% accurate in the very first tip off, in the very first shot. Okay, so it means that I need to minimize my loss. I need to minimize the value of a loss, and for to minimize that loss I need to update my weights. Okay, so weights are nothing but these values. Okay, so weights are nothing but these values. So I need to update my weights, and with the updated weight again I need to do this calculation, the calculation of forward propagation, and again I need to calculate the loss. Now I need to check whether my loss is like reduced in comparison with the prior loss or not. Okay, so in that way I need to minimize the loss. I need to minimize the loss, and that process of minimizing a loss is called a back propagation. Okay, so I think we understand forward propagation, and we update the parameter with the help of an optimizer. So now it's time to understand a back propagation. So for back propagation you need to understand a very important thing which is called a chain rule of derivative. Okay, so maybe definitely in our childhood we have learned about derivations. Okay, so we learn about derivations and all these things. So now the very first thing which we need to understand is the chain rule of derivative, that how we need to find out the derivative of any function or derivations of anything. So that is what we need to understand, and with that I'm going to calculate the equation, or I'm going to find out the values for a back propagation. Okay,
So,
so now come on to the back propagation. And guys, don't be worry about like activation function, optimizer, and loss function, because as I told you that I will take those things in a separate, about a different kind of an activation functions. What is like the role, and what may be the a kind of a drawback and importance of like each and every activation function. The same thing for a loss function and as well as an optimizer. Okay. Although in case of a forward propagation and a backward propagation, we can see that these things are really important. So in case of a forward propagation, we already observed the importance of activation function, and even we can see that we get a loss at the last. So that place a loss function is important. And now like in case of a backward propagation, optimizers are important. Okay, so we are going to discuss all these three terms in a separate, maybe today or not like today, so we'll discuss it like tomorrow, before going into like a hands-on of your case study. Okay, because even the case study is very simple. Okay, so don't worry. So and even we have I have that extra hours in my hands, so don't worry about like anything. So come on to the back propagation. So in a back propagation, yeah, before going through a back propagation, one thing which you need to know. So just like I took an example of XOR and 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 all, before just for a motivation. So in a back propagation we need to find out the derivatives. Okay, so we need to find out like a lot of derivatives. Okay, because in an optimizer what happens, so like just let me give you the scenario, otherwise maybe you're not able to not able to make a connection. Okay, so in a back propagation, okay, so here we get a loss. Okay, so we get a loss. Now suppose if you are aware about any optimizer, like a gradient descent is a very like a popular optimization function. Okay, so yeah, just let me know that if you're guys aware about gradient descent, or yeah.
sir, we learned the surface level theory of it, but we didn't learn the actual
Yeah, so
maths.
surface layer theory is fine. So you learn a surface layer theory, maybe you've seen like this picture of like gradient descent optimizer. Yeah,
Yes, sir.
yeah, where our objective is to reach at this place. Okay. So our objective is to reach at this place. So this is considered to be a global minima. Yes. So fine. This is the only thing I just want to know. Okay. And then at the top, so maybe my loss is very high. Okay. So maybe I'm somewhere over here. Okay. So maybe my loss is somewhere over here. Now I need to minimize it. Okay. So I need to minimize it. So don't worry about that mathematics. I will tell you about like that particular mathematics. Don't worry about that. But yeah, this is how I just try to gradually try to decrease my loss. I just try to gradually decrease my loss, and my goal is to reach at this position where the loss is minimum, which is very much very near to zero. Okay, where the value of loss is very like near to zero. Okay. Now, in order to get this loss function, we are trying to update my weights. Okay, we are trying to update the weights. Now, how we can update the weight? So, in order to update the weight, maybe so this is like a new weight which I want to find out. So, I can try to update on the basis of the old weight. Okay, old weight minus learning rate into del L. L is nothing but a loss upon del W. Okay. So this is guys, this is the equation for del for a new waves. Okay, so this is the equation for a new wave. So maybe so definitely we have a value of my older weights. Okay, which we have considered at a time of backpropagation, and we need to find out the derivative. Okay, so in order to find out derivative, we need to understand that chain rule of derivative, that how we can do a differentiation. Okay, so maybe most of you guys already know or already like even remember that how we can do a how we can find out the differentiation. But like yeah, maybe if you guys are not remember or maybe not able to generalize it, so I will take some like very easy examples to understand that how to find out the derivative. Okay. So yeah, guys, this is a formula for a grade. This is a formula in terms of an optimizer. Okay. So this is the thing which we need to where we need to find out the derivative. Okay. So this is the formula for a gradient descent. Okay. So this is a mathematical representation of that. Even we can try to update the bias also. Okay, so maybe suppose if you think that a bias is also important, and we need to update the weights of a bias, so in a similar way we can try to update the weights of a bias also. Okay. Yeah. So this is a formula for a gradient descent. Okay, and this is what we call a learning rate. Okay. So this is what we call a learning rate. Okay. So I will so I will tell you right now that what is a learning rate. So learning rate is nothing but it's you can say that it's a controlling parameter. Okay, so which actually controls like the speed of your convergence. Okay, so convergence means we are trying to reach over here, so we are trying to converge. Okay, so we are trying to reach over here, it means we are trying to converge from this position. So we are trying to make this kind of a graph, we are trying to get this kind of a graph, this kind of a like a convex curve, I can say. Okay, so I just want to have this kind of a convex graph or convex curve. So I'm trying to converge. Okay, so from this position to this position. So in order to make our convergence smooth, okay, in order to make our convergence smooth, like it should not be a very fast, and even it should not be a very slow. So in order to make it optimal, I need to use this learning rate. Okay, so this learning rate is nothing but it's a controlling parameter which controls this level of convergence. Okay, because we don't want to come like very quick, we don't want to come like very fast, and even we don't want to convert very slowly. Okay, so both the things we can't tolerate. Okay, because suppose if we try to convert very fast, so it may possible that my like value can overshoot. Okay, so if I try to convert very fast, so it can overshoot, and my model tries to maybe overfit. Okay, so I can go like even so if this value goes in this direction also, then also like the value of loss or the value of error will increase. Okay, so it might overshoot if I try to increase the value of a learning rate, if I try to convert fast, and if I try to convert slowly. Suppose if I try to make this value as maybe 0.0000001, so then it tries to convert very slowly, and in that condition, what happened in that condition, like my model becomes computationally expensive. Okay, so it will become more and more computationally expensive. So even I don't want that. So both the condition is not is not good. So even like a faster convergence and a slower convergence, both are like dangerous, and both are not like something which we don't want to have. So that's why, to make this convergence optimal, we use this learning data. Okay, guys. So the idea of this learning rate is clear.
Yes, sir.
Okay. Now come on to the chain rule of derivative. So let's get into the chain rule. So I just start with a simple problem. I'm going to start with a simple problem. I can say a simple example. So suppose this is my like a function which is nothing but x plus y into z. Okay. So if I try to represent this thing in a computational graph, so it can be x, and then it can be a y, and it will become x plus y. Okay. I can, so this is a representation in a computational graph. Okay, then my f will be nothing but it will be a u into z. Okay, guys. So yeah, you can take any value to make this calculation. Suppose if you take a value of x is 1, then y is 2, then z is 3, then the final calculation will be 9. But I don't have to take anything with that. Okay, I don't have to take anything with the calculation. I just need to tell you about a like a chain rule of derivatives. So now if I want to find out three derivatives, so suppose if I want to find out three derivatives with respect to this function. So if I want to find out del f upon del x, del f upon del y, and del f upon del z. Okay, now what this chain rule states that, so means if I want to get back onto the x, okay, so del f upon del x means, so just like in case of a w, so we try to get a new w, the new value of the weights. So just like that, I want to get back onto the this x, means I want to I want to have a new value of this x. Similarly, I want to get back to this y, and the same thing for a z. Okay, so this is my path. Okay, so maybe I can try to represent this thing with a different color. Okay, so this may be my path of a return. Okay, so this is my path of return for x, y, and for a z. Okay, now if I want to find out del f upon del x, so what path I am following? So for del f upon del x, what path I am following, guys? So I'm going through what is this f is, so this f is nothing but u into z. Okay, it means and I'm following this path where this u like comes. Okay, so it means that I'm going through this path, I'm going through this path. So this will be nothing but del f upon del u into del u upon del x. Okay, and finally it will give you a del x del f upon del x. Okay, so now if you calculate it, so del f upon del u becomes what? So I think you are aware about the differentiation, so I'm just giving you a chain rule. So del f upon del u is nothing but z. Okay, and del u upon del x. Okay, so if I calculate a del u upon del x over here, so it will be nothing but 1. Okay, because this is a single value, so it will be nothing but 1. It means my del f upon del x is what? Z. Okay, similarly, if I try to find out a del f upon del y, so what it will be? So it will be a del f upon del u into del u upon del y. Now again the calculation will be nothing but u. So the answer will be u over here. And in a similar, oh, sorry, answer will not be u because okay, sorry, here also we have a same value, so the answer will be z again. Okay, and now with respect to del f upon del z, so it is fine because we don't need to cross any path, so this is going to be u only. Okay, so del f upon del z is nothing but you have u. Okay, because you don't need to like cross any path. Okay, so this is a final equation for sorry, this is a final value for this function. Okay, so for del f upon del x we have z, for del f upon del y we have again z, and for del f upon del z we have u. Okay, so is this calculation is clear, everyone?
Yes, sir.
Yeah, guys, any doubt?
Hmm.
Don't be shy. Okay, so if you have any doubt, just clear it out right away, because the same ideas, the same chain rule, we are going to import on our the main function with our main forward propagation equation. Okay, okay, so let me take another example also. So suppose like if anyone like feeling that okay, so maybe they're not very much clear with this example, so I will take another example, don't worry. So let me take another function for you. Okay, and even I will try to extend your path. Okay, because in case of neural network your path can be like a long. Okay, it can be a 3 layer, it can be a 4 layer. Okay, so let me take a more around a 2 layer path, or maybe a 3 layer path, because maybe this is a single layer perceptron. This can be applicable for a single layer perceptron. So let me take like a long route for x and y. So again we are having an x over here, again we are having a y over here. Let me connect this. Okay, because we have an x and y. So u is equals to x into y. Okay, then we have a z over here. Now x, y plus z, it means u and plus z. Okay, so v is going to be u plus z. And finally we have f, where f is equals to nothing but 5 plus 2. Fine. Now again if I want to find out del f upon del x, del f upon del y, and del f upon del z, now what will be the calculation? So suppose if I want these three values, so if I again take a root, so for x I need to go in this way, I need to like follow this path, I need to go in this way. Okay, similarly for y also I need to go like in a similar way. Okay, so this is like multi-layer. Okay, we have 2 layers over here, and for z it will be a single layer. So okay, now if I write it down, with respect to the x. Okay, so what will be my like calculation? Okay, so if I write it down with respect to the x, so del f upon del x is going to be what? Del f upon del x is going to be nothing but del f upon del v, then del v upon del u, and del u upon del x. Okay, now if I try to calculate it, so del f upon del v is what? This is going to be a 5. Del V upon del U is what? So del V upon del U is nothing but 1. And del U upon del X is going to be del U upon del, okay, del X, 1 second, del X is going to be Y. Okay, so it is going to be 5Y. Similarly, for our del F upon del Y, again, we are going to follow the same path, just in place of X, it will be Y. So my answer will be 5X. And for del Z upon del X, my equation will be nothing but del F upon del V. Yeah, and then del V upon del Z. Simple. So this is going to be 5, and del V upon del 1 second. Yeah, del V upon del Z is going to be oh no, it's
Sir, how did del F come here?
where del F.
Sir, del Z by del X is equal to del F by del V.
Del G by del. Okay, sorry. This is, oh, you need to correct me over here. Na? Del. This is nothing but this is del F upon del Z. Na? Okay, now it is correct.
Okay. Yes, sir.
Okay. So yeah, this is like your calculation. Okay. So yeah, this is how our chain rule of like derivative work. Okay, so we need to so this is the same, so the same idea, like on the same idea we are going to perform our back propagation. Okay, because in a back propagation also we need to calculate in a backward direction. Okay, so we are going to calculate in a similar way. We are going to calculate in a similar way. We are going to find out a derivative in this way. Okay, so there you need to adopt this kind of a rule. Okay, this is nothing but a chain rule. Okay, del F upon del V. So you need to understand, you need to clearly understand the path. Okay, like from which path is actually responsible for taking me giving me my output, giving me the value. Okay, so guys, let okay, so just for me, because okay, maybe some of you like still some of you is not able to make this out, make able to maybe understand this chain rule. So just try to do like one example. Just try to do this example by yourself. Okay, I will definitely tell you the answer, but try to do it by yourself. Okay, so 8x plus y. So 8 is nothing but it's a number, so even you can ignore it. Y plus z, and plus 1 second, plus yz. Okay, so just try to do it by yourself. Again, it will be a del f upon del x, del f upon del y, and del f upon del z. So these three things I want to have. I want you to find out. Okay, you can consider it u, v, and w. Okay, or you can take it. You can take your own variable. I don't have any issue with that. Okay, so if you want, you can take a, b, c, and 1. It's your matter. Okay, but yeah, the final answer will always be in a form of x, y, and z only. You know that. Okay, so yeah, just try to find out this thing with the chain rule. Okay, del f upon del x, del f upon del y, and del f upon del z. Okay, try it out, guys. Okay, so you have 7 minutes. Just try to find the answers.
Sir, is this a 6 at the beginning?
No, this is 8,
Okay, okay, okay.
and it's just a number, so even you can ignore it. Okay, guys, is it done? No.
Yes, sir.
Okay, so done. And then what is the answers of like these derivatives?
Dou F by dou X is 8 times W, sorry, Y square Z plus YZ square. And dou F by dou Y is 8 times, it's actually the same as dou U by, sorry, dou F by dou X. And dou F by dou Z is 8 times Y square plus Y times X plus Z plus xz.
Okay, is there anyone else who did this? Maybe I think you didn't break it anywhere, or like take a long way or something. Let me draw a computational graph. I think it will be much easier for you. Okay, so this is fine. Okay, so I can take a y over here. Fine. This is how I can make for x plus y. Yeah. Then the second one is y plus z. So that I want to store in maybe a v. So y, I already have a y. Then we have a z over here. Okay, fine. Then I need to multiply it. Okay, so I need to multiply it. So I can take it as maybe again I can take any value, maybe a, where I'm multiplying these two value u and v, u into v. Okay. So yeah, you guys are free to take any value, any variable, that is fine. Then y into z I'm taking. Okay, so uh, okay, so z I'm having over here, and it will be inside a w. So w is equals to y into z. So z I'm having, now I need to take a y from here. Okay, fine. So this is great. A equals to uv, and now u into v plus w I need to make. Okay, so it means I need to take one more root form here. It can be in this way, and I can take a variable b, and inside this b, because here I take a, so I take a v over here. Now it can be a plus w. Yeah, fine. And then finally my f will be 8 into b. Yeah, guys, this computational graphs make sense, correct?
Yes, sir.
Okay, now let me show you the root first. Okay, so for del f upon del x, I need to follow this route. I need to cross this b, then I need to cross this a, then I need to cross this u, and then finally I will reach over here. Fine. Then the same for y. Okay, so I need to cross. Okay, so it will be multi-layer again. So 1, 2, 3. Okay, so we have 3 layers, and the last one, again in the last one also, I think I have 2 layers. Okay, fine. Is this path correct? Yeah.
Yes, sir.
Now let me find out del f. Okay, so I will create a line over here so that you guys not confused. Del f upon del x. So what will be the del f upon del x? Okay, so yeah, just tell. Okay, who were like done it. So just tell me what is del f upon del x. It will be del f upon del b first. Yes.
Yes, sir.
Okay, then the next del b upon del a. Correct. Then del a upon del u. Okay, I'm just following this path, nothing else. And then finally del u upon del x. Correct. Yeah.
Yes, sir.
Now let me know the values. Okay, so del f upon del b is nothing but 8. Okay, this is 8. Del b upon del a, so this is nothing but 1. Yes.
Yes, sir.
Then del a upon del u, so del a upon del u is equals to like b. Yes, because it is in multiplication. And then del u upon del x is what? So del u upon del x, so this is nothing but 1. Okay, yes, correct.
Yes, sir.
So what will be 8 into v y plus z? Yes.
Yes, sir.
Okay, so can you rectify your like mistake that where you get like a wrong value?
Yes, sir. I by mistake, I assumed u, v, and w are being multiplied. The final yz term is an addition. That was my
Okay.
mistake.
Okay, so now this calculation is clear to everyone, guys. Please acknowledge me. For everyone, this calculation is clear because with this I just take like every value one by one. I take like every value. So now this calculation is clear to everyone.
Yes, sir.
Yeah. Anyone having any doubt with this calculation? And the similar equation in a similar way you need to calculate for y and z. Okay. Even in z you just have two layers. Okay. It means instead of four values you just have three values over there. Okay. So even for just for like sake of you, I will calculate for del y. Okay, or I del z, because in del y you need to follow the same path. Okay, so I will take a del z so that you guys are not confused. So del b, then del b upon del w, and then finally del w upon del z. So now if you calculate it, so del f upon del b we already find out. Okay, 8 del b upon del w. So this is also we already get. Okay, 1, and then w upon del z. So del w upon del z agar we do, so it will be y. So the answer will be 8y. Fine. Okay. Okay, guys.
Yes, sir.
Okay. Now, okay. So I think now this chain rule is clear to everyone. So now by taking this same knowledge, okay. So now just take the same knowledge for a backpropagation. So I will give you the value which I need to find out in a backpropagation. So with that value, just try to calculate the derivatives. Okay. So now come on to the, okay. So I think first, okay. So just let me write the forward propagation formula first, because from here itself I can I can go with the loss function. Okay, so this will be my z, which is nothing but w1x plus b1. Okay, and y hat can be written as a1, which is nothing but a sigma of z1. Now I need to get this sigma, or I can write a g over here for activation function, because activation function can be anything. So the loss is nothing but, okay, so I'm going to consider negative loss function. Okay, so guys, you are I think you guys are aware about a log loss function. Okay, maybe you have learned this thing in a logistic regression, log loss function.
No,
Okay.
sir.
You're not aware about a log loss function.
So we learned logit function. We don't know log loss.
Yeah, logit function. So you that both the things are very much similar. Okay, so logit function, you know now.
Yes, sir.
So what is that logit function?
It is the log of the odd of an event happening. Basically, log of p divided by 1 minus p.
Yeah, so 1 minus p. So even it can be written like if I just consider that like a simple value from there, so it can be written as minus y log of y hat. Yeah, I think you learn about this function, y into log of y hat. Okay, then okay, so if minus is outside, so it will be plus. So 1 minus y log of y hat, log of 1 minus y hat. Okay, so in place of y, it may be like p also, because p is a representation of a probability. Okay, so this equation we have learned now.
Actually, no, sir.
You may definitely learn, but maybe you forgot or you miss it somewhere. Okay, just okay, don't worry about that. Okay, so okay, I will take like a loss function, because even as I told you that I will talk about the different loss functions. So for now, just take like a very simple loss function, so that we can that will make my calculation easy. So in case of a neural network, the easiest loss function which we can choose is nothing but it can be my loss function. Okay, minus y log of y hat. Okay, and now you know that this y is what? This y is nothing but actual label. Okay, this is the actual label, and this is what? This is a predicted label. Yes. Okay, I think you guys are not confusing in like y and a y hat. Definitely you know about a y hat. Y hat is nothing but a predicted value. Yes.
Yes, sir.
Okay, so this is a simple loss function, like easiest loss function I can say. So this is like in case of a classification. Okay, so in case of a classification model, this is how I can write this thing. Okay, so even like in place of y hat, I can write like a of 1. Okay, so both the things are same, because whatever the output I am getting from that a1 or a2, so that will be my predicted value. That will be that is my predicted output. Yes, correct. Okay,
Yes,
so
sir.
the loss is nothing but minus y log of y hat. Fine.
Yes.
Okay, so just try, let's try to differentiate. Let's try to get like differentiation value. Let's try to get our the value from a backpropagation by using this loss function. Okay, so again in a similar way, because we want to make it a simple, we want to generalize it for multiple layer and multiple nodes, so we want to make it a simple. Okay, so always try to make it a simple. Okay, so guys, like my mentor, okay, who are always trying to teach me, who actually teaches me, so he always say that don't try to be don't try to be like a phantom in one shot. Always try to take a very easiest path. Just try to do with a single example, and then try to generalize it. Okay, so the same thing I'm going to do over here. The like in a similar way, I think we have learned about a forward propagation. So the same thing I'm going to do with a backward propagation. So let's take a single layer example. So this is my input maybe. Okay, and I'm making in sense of a computational graph. Okay, only because it is simple to like build. Then we have a1 over here. Now my loss function is giving me what? Okay, so it is giving me a1. A1 means y hat. Okay, so with the loss function, where I need to make a comparison, so I need to make comparison between two values. Okay, y hat and y. Okay, so this is nothing but a y hat, and this is actual y. Yes, means a predicted value and a correct truth value, truth level. Okay, so what are the things I need to calculate? Okay, so now guys, just try to understand in terms of a chain rule. Okay, because you already know these things. So here also I need to calculate three things. Okay, so the first thing I need to calculate is nothing but del a1 upon, sorry, I need to calculate sorry, with respect to a loss. So you can consider this loss as f. Okay, so I need to calculate del l upon del a1. First thing, very important. Then the second thing, second, because okay, here we have a w, so I missed that w, guys. So here I have a w, and here I have that b1. So the first thing I need to calculate this. Then the second thing I need to calculate this del l upon del w. As I told that I need to update this loss. So I think you know about this equation. I already write this equation in front of you. So I need to find out this value. Okay. So whatever I'm doing, I'm going to find out that value, because rest of the values you already know. Okay. Because learning rate is your hyperparameter, and I think you know that how we can get an optimal value of hyperparameter. So there are like two ways. One is cross validation, another one is hyperparameter optimization. Maybe a grid search, randomized search CV. Yeah. So that are the different topics. Even if you don't know, so I will teach you those things. Don't worry. So del L upon del W, and here we have del L upon del B. Fine. Okay. So I need to find out these three things, and you know that in actual sense we need to find out this in order to update my parameter. So I need to get the value of this, and I need to get the value of this. Okay, and definitely this value is going to play a very important role in order to get the value of del L upon del W and del L upon del B. Fine. So let's calculate. Let's first calculate del L upon del B. Okay, so let's calculate it. Now, in order to get del L upon del B, what route I need to find? Okay, what path I need to follow? Okay, so I need to follow this path. So I think if I want to reach over here, if I want to come over here, so I need to go through this path, means del L upon del A. Even I need to follow, I need to go through this also. Okay, because without considering Z, I don't think that I can reach to B. Okay, so del L upon del A of 1 into del A of 1 into upon del Z into del Z of del B. Correct, guys?
Yes,
I
sir.
think this is this is I am getting from a chain rule. Okay, and now I think you guys are very much familiar about a chain rule. Okay, so this is maybe my equation A. Okay, now let's find out del L upon del A, because I need to get this value, then only I can make this calculation. Okay, so let me calculate del L upon del A. Now how I can calculate it? So L is nothing but L is minus y log of, okay, and it can be written in this way. It can be written as A1. Yeah, it can be written in this way. Yes. So if I try to find out a differentiation of this, so I think if you know the differentiation of log, so log differentiation of log is nothing but upon. Okay, so differentiation of any value with respect to the log is nothing but 1 upon x. Okay, so suppose if I want to find out the differentiation of this value, so this is nothing but 1 upon x. Okay, so in that manner, if I want to differentiate, so minus y log of a, it can be written in this way. So a, okay, fine. So this is the value of del a del L upon del A. Now this is my equation B. Fine, guys.
Yes, sir.
Okay, now come on to the third okay, now let's find out this value. Okay, because this value is done, we will done with this value. Now let's get this value. So del A upon del Z. Now how I can get this value? So I think this is something which we have already written. So Z is nothing but, okay, so if I try to, okay, so this is what we are trying to differentiate. Okay, so a1, so a1 is nothing but g of z of 1. Okay, so g is nothing but a activation function, so it can be any activation function. So now if I want to differentiate, so I can write it this way: g dash, okay, g dash is the representation of differentiation, and it will be my equation C. Okay, so yeah, I get the value of del A upon del Z also. Fine. Now the third value is very important again. Okay, so del Z upon del B. Now how I can get the value of del Z upon del B? So for that, I think I need to know the value of Z1 plus. Okay, so the value of Z is nothing but W X plus B. Okay, and it will be a W transpose, I guess. Okay, so if I try to make a differentiation with respect to this, so del Z upon del B is going to be what? So one second, del Z upon del B. Okay, so we are not going to get nothing over here. Here we are we are getting just one. Okay, it means del Z upon del B is going to be what? It is going to be 1, because here we this value becomes 0, and here we'll get 1. Okay, so this is my equation D. Now using A, B, C, and D, using all like A, B. Okay, so not A, B, C, A, B, C, and D. Okay, because A is this. So just try to put the value we are obtaining from B, C, and D. Okay, so B, C, and D. What will be my output? So del L upon del B is going to be what? So this is going to be nothing but, so the first value is minus y upon a of 1. Then the second value is going to be g dash z11. Okay, so this is going to be my calculation. And guys, this multiplication, okay, so this multiplication, because like the shape of both the values are same, 1 cross m and 1 cross n, but then also we are able to do this calculation because this is called Handomad Handomand, I think, matrix multiplication. Okay, so this is going to be your del L upon del B. Now, in a similar way, I can get the value of del L upon del W because that is more important, because even sometimes you can see that we are not using bias, but weight is necessary. Okay, we are going to use weight everywhere. Now, with respect to the weight, okay, with respect to with the weight, okay, so suppose if I try to find out del L upon del W, so with respect to the weight, I think everything is going to be the same, okay, because the path is same, okay. So if I take a path, if I try to get a path, so path is going to be the same. One second, yeah. So even here also we have del L upon del A, we have del A upon del Z, and then we have del Z upon del W. Okay, so even the complete path is same, and first two values are also going to be same. Okay, so the first two values are also going to be the same, but this value is going to be changed. Okay, so last time here we have Z is equal to W1x plus B. Okay, so last time we have 1. Now this is going to be del Z upon del W. So last time we have uh, del B upon del Z upon del B. Okay, that's why the output is 1. The calculation will be 1. But now this time we have del Z upon del W. Okay, now with what is this del Z upon del W? So this is going to be, okay, so this side we have 0. Now this side we are having at least some value. Okay, so we are having x. Okay, so we are having x. So everything is going to be the same, so everything is going to be same, but at last we are going to multiply with the x, and not even x, it will be a x transpose. Okay, so minus y a11 into g dash z11. And because from here we are doing again the same matrix multiplication, so here we are getting 1 cross m, so that's why we can't take like n cross m. Okay, so we need to make it m cross n, so that's why I need to take x transpose. Okay, then it will become okay, instead of n cross n it becomes m cross n. Okay, now we can multiply it, and here we'll get a final value. Okay, so now we get both the values. Okay, so I think now you can relate that we want two values. Okay, so I think now you can relate that like W new is nothing but W old. So W old is is something which you already know. Learning rate is a hyperparameter, so you can set it to maybe 0.1 or 0.5 anything. And del L upon del W. So this is the only thing which I need to find out, and yeah, we'll get this. Okay, and similarly for beta nu, similarly for bias, uh, okay, similarly for bias, we want to have this value. Okay, so yes, we have this value also. Okay, so we have both the values for to calculate our back propagation, to calculate to make a calculation in back propagation. Okay, now I'm going to generalize. Okay, so I think now you guys have a clear value. Now you guys have a very like you guys can relate that to how we are getting a value in case of a back propagation. So I'm going to relate this thing, I'm going to like generalize it for multiple layer, or maybe for just two layers. Okay, so uh, even for two layers. Okay, so yeah, okay, even for two layers, what you need to do is, so now guys, this is not going to be tough for you at all, because for forward propagation you already know the like a formula for a two layer. Okay, so even in case of a backward propagation, you know that the output of the first layer becomes the input of the second layer. So the similar thing is going to happen in a back propagation also. Okay, so let me write a forward propagation on one side so that you can understand easily, and the back propagation on this side. Okay, so for forward propagation, what is my equation? So I'm going to write the same equation which I have written just like R back. So this is going to be this, and this is going to be G of Z1. Okay, so this is going to be like equation one. Equation one means for the first layer. And then for the second layer, this is going to be Z2, W2. Then it will not be X, it will be A1, and then B2. Okay, and my A2 is nothing but G of Z2. Fine. And now for a back propagation, what going to be happen? So we are going to find out the back propagation from this place. Okay, so from this place. So we need to find out del L upon del A1, then del L upon del RW, and del L upon del B for the first layer in the backward direction. And for this, I'm going to find out del A upon del 2. Sorry, this is for the first layer in the backward direction, and this is the second layer. Okay, fine. Okay, so here the value is not going to change. Here the value is going to be the same. Okay, so this is how we can do in calculation now back propagation. Okay, so everything is going to be the same. Just like we need to find out value in a like a backward direction. Okay, so I think yeah, it is going to be same del L upon del A2, then W2, then B2, then A1, W1, and B1. Okay, and you know that for updating a parameters, I need to find out del L upon del W and del L upon del B in order to update a parameter with the help of a gradient descent. Okay, so this is what we need to do in a back propagation. Okay, so like if you even if you can try to see the same thing, you can try to generalize the same thing with a computational graph of like a back propagation. Okay, so even I want to, even I need to share that like a PDF with you. So let me open it so that I can show you that computational graph, and even I will share it like right away. One second, just give me 2 minutes.
So here, why are we taking del L by del A actually?
Del L upon del A actually you are taking, but without that value, it is not possible to make a calculation. Na? How you are able to find out del L upon del W without del L upon del A?
Okay. Understood.
Okay, so even this is a very important question from an interview point of view, because like sometimes it is asked. This question is asked like is activation function play any role in a back propagation, or like activation function is important in a back propagation or not? Okay, so yeah, definitely it is important, because you need to like you need to consider that activation function also. Without that we are not able to find out uh, the what we are not able to find out our weights and biases. Yeah.
Yes, sir.
Okay, so even I will show you. Okay, so this is a, okay, so guys, I'm okay, even you can go onto the internet and check, but because I will share this whole PDF with you. So this is my own like handwritten notes, guys, so you can see that. uh, yeah, in a backpropagation. Yeah, this is this is a graph. Okay, so you can see that this is a computational graph. Okay, so del L upon del A2. So yeah, in a similar way. So in so in a same order. So in a order in which we get a value for a forward propagation. So in a similar order, we are trying to get a value for a back propagation also. Okay. Yeah, guys. Any doubt?
No, sir.
Okay, and I'm talking about this log loss function. Okay, so maybe okay, so this although this function is fine if you like able to generalize, or if you're able to make a equation with this simple function also, so that is also a fine. But the main official function is a sigmoid function, or you can say a cross entropy loss, or this loss function. Okay, so this is what like guys I'm asking about. So this is a log loss function. Okay, so this is what we call as a log loss function, negative log loss function. Okay, so you can see that we have minus y, then y. So here minus y is nothing but actual output. Then this is a predicted output, and because it is maybe they are taking a two layer, so that's why here we have a notation as two. Then 1 minus y, it means this is for another class. Okay, so this is simple for a binary class, because sigmoid can be used for a binary class only. Okay, so this is for a binary class, so that's why we have like 1 minus y and 1 minus y hat. Okay, so a2 is nothing but a y hat. So this is a probability for like one class, and this is with respect to the another class. So in order to make your gradient function convex. Okay, so in order to make that optimizer convex, because in case of mean square error, okay, so like we'll get a convex curve. Okay, we'll get a convex curve if it is a regression task. Okay, where my predicted value can be any continuous variable. Okay, so if my predicted value is a continuous variable, so it will be a so with the mean square error, I will get a convex graph. Okay, but if my predicted value is not a continuous random variable, if it is a discrete random variable where it is maybe a 1 0 2 3 for a multi-class, so it may be a 0 1 or anything. So in that condition, my graph will not be a convex. Okay, my graph will not be a convex. I will not get a convex graph with the help of a mean square error. So that is why I'm using this log loss error. Okay, so this equation, guys, this equation is nothing but a log loss error. Okay.
So this loss function works even for multi-class classification.
No, this function is for a binary class.
Okay.
For a multi-class, we are going to use something called a softmax activation function.
Okay, sir.
Okay, so like we can generalize it. We can generalize it for like a multi-class, but this is specifically, you can see that this name. So this is specifically is for a binary class. Okay, like for a multi-class, the name will change. It will be categorical cross entropy. So instead of, in place of a binary or a sigmoid cross entropy, which I have written, it becomes a categorical cross entropy. Okay,
Okay, sir.
where we may have like multiple classes, right? So the same generalization, the same thing we have like I have done over here, which I already show you. Okay, so even guys, I think this is something started from uh, okay, page number 28. Okay, so one second, let me check. So this is just written work I have done. So page number, I think this is 35. Yeah. So from page number like 28 to 35. Okay, so let me download it also. Let me share it right away, because maybe I can forward. Yes, so So neural network, I just save it. And okay, in a chat box, yeah, we have this file sharing option. Uh, Create Zumba downloads. So guys, I just send it. I think yeah, now you can download it from a chat box. Okay. Yeah, guys, you have received this note.
Yes, sir.
Okay. So okay, guys. So this is like kind of you can like call it as a homework for you. So what you can do just for like a page number 28 to 35, just try to understand this equation, because this equation is very much similar to what we have done so far, because you can see that we are doing the same calculation over here. So nothing advanced like calculation I have done over here. So just try to generalize it, okay, and just try to read and just try to get some more information, because as you told that you didn't learn about a log loss error, but it's a part of a logistic regression itself. Okay, so just for that reason, I just want ask you that try to get some more information about log loss error. Okay, definitely if you guys not able to get those, so tomorrow as I told you that I'm going to take a loss function and all those like a function. So definitely I'm going to talk about those things also. But just for like knowledge, that if you try to get some more information, it will be a good for you. Okay. So the two things you need to do, so just try to go through the equations between page number 28 to 35 first task, and the second try to get like more information about log loss error. Okay, fine.
Yes,
Yes,
sir.
sir.
Okay guys, great. So now let me see. Okay, so 1 second. So still we have a time now, guys, or we need to wrap up. Hello.
Sir, come again.
Uh, we have okay, so we have some more time, or we can wrap up now.
So usually around 5:50 we wrap up.
5:30.
5:50.
Six.
50.
Okay, 5:50. So just 3 minutes. Okay. So okay, guys. So just wrap up for today. I just maybe I just try to take one more thing, but let me put it in tomorrow's agenda. So tomorrow, I think we'll start with your with your task. Okay, with this log loss error, and then we'll go through the activation functions, optimizers, loss functions, and as well as before okay, in between like I will tell you about something called as a gradient okay, vanishing gradient problem. Okay, so one very important problem which might occur and you may encounter, which is called a vanishing gradient problem. Okay, so this is we are going to discuss tomorrow. Okay, so we are going to start with these two, and then I will cover like optimizers and all those critical parts. And then tomorrow we'll also do like a coding session. Okay, we'll also do like a hands-on code on a case study. Okay.
So
Yeah.
for the hands-on code, are we going to be using any packages like TensorFlow or something?
Yeah, TensorFlow and Keras.
Okay, sir.
Okay. So we'll do tomorrow like with that Amnish data set, disease recognizer. Okay. Although that data set is already available inside a Keras, so you don't need to download it maybe from Kaggle. So we'll do it by taking it in a Keras itself. Okay.
Okay, sir.
Okay, guys. So thank you so much